So this presentation is called Awareness and Recovery, and what we're going to talk about is the converter failures and how they're related to the downstream electronics and the hydraulic controls for them. So we're going to be using a lot of physical parts as well as some screen PowerPoint. But before that, just do a quick introduction for myself. I'm with Sonnax, Vice President of Technical Development, and I've been with Sonnax now for 21 years, and I've worked through a lot of product development both with the torque converter side and also with the hydraulics. I work with a great bunch of engineering staff and product development people. Prior to that, I was with a volume remanufacturer, and prior to that, I was a shop owner. I've been an automotive instructor, and I started in the industry in 1974, actually. So that's some of my experience there. I want to give thanks to ATRA primarily because of putting this together and all the years that they've been working with the industry. Secondly, I want to appreciate SIU, and Sean Boyle has been putting this program together with me here the last couple days. Does an excellent job, so thanks to SIU and Sean. And then lastly, I want to thank Certified Transmission because they've sent a lot of cores and a lot of samples of that we're going to go through today. And so Jeff Stuck is the one that put this the cores and those samples together. So thanks, Jeff. Okay, so this material is, I called it Awareness and Recovery. And the reason I did that is awareness as to why converters fail, where the material is coming from, and recovery, and that is to recover from damage, recover from the failures so it doesn't happen again. We don't have repeat failures. And so this is a 2020 division into torque converter failure. Okay, so where did the material come from? So a lot of times you take the pan off and you say, okay, well, what is this? Is this paper? Is it clutch coming from the transmission? Is it converter material? So inside the converters, which we'll show you here out in a few minutes, is that we have aluminum material in there, we have steel ferrous material, we have paper composite, we've got phenolic plastic, we've got woven carbon, and there's a way to detect every one of these when it's in the pan and in the transmission. So I'll show you that here in a couple minutes. Where did this material end up? So that's the next thing, is if it came out of the converter, it went someplace, and I believe most of you know at this point it goes to the radiator. From the radiator, it's going to come back, and next path is into your bushings. So it starts to take the bushings out, usually from the back first, because we know that how it exits right at the rear of the case coming into the bushings. Okay, so after we find out that the converter failed and we isolate where this material came from, we try to figure out where did it end up, which is the cooler. So now we flush the cooler. And how do we know if the cooler is sufficiently flushed? So one of the steps I'd like to cover today is the opportunity of using the SonaFlow. And I'm not going to go through all the charts, but I do have examples of what is good and how the flow should pass through and how you can tell if the clutch is applying properly. And also, when you're doing a flow test, we'll get into on isolating whether a converter is a 2-path or a 3-path converter. And there's a big difference in diagnostics on those. Okay, and we're going to end up then talking about some solenoid issues. So when you pull the speed sensors out of the inside of the transmission, what you're going to recognize is you have a lot of times there's fuzz on them, and that fuzz comes from the magnetic debris that's coming from torque converters or planets or whatever has failed already. So that same fuzz that you're seeing metal debris on your speed sensors is also going inside your solenoids, and it slows them down. And I have pictures and slides coming up here that shows you what happens internally inside those solenoids. Okay, so what we're going to do first is review different types of torque converter designs. And one of the most popular ones that we're dealing with today is the 6L90. So we're going to start with that one first. And then we're also going to talk through the 2-path and the 3-path. And again, like I said before, the differentials between those. We're going to talk quite a bit about different types of pressures that influence inside the converter. We've got apply pressure, release pressure, we've got clamping pressure, basic components of the converter. Now this is a 2-path converter, and you can see this is the cover, and here you can see the mounting pads as they run radially around the outside. And then you have the clutch, that's this purple part right here. Okay, that's the clutch that applies, the lockup clutch. This is part of the damper assembly, this blue. You've got your damper springs. That's in the white right here. Now most of these late model converters they call it dual dampen, which means it's going to use the damper springs on the apply side in the lockup portion. And also when it's locked up on deceleration, the damper runs back the opposite way. So now instead of the engine driving through the springs, when it's locked up, the rear wheels are driving the turbine through the springs through the cover. So a dual damper has spring deflection on both sides of it. And I'll show you some examples of that. Okay, this is the turbine hub right here in the middle. And then we get into the turbine shell right here, turbine blades. And I'll talk about different types of turbine blades. I'll show you the difference between the typical stamped and the furnace brazed turbines. And then we move into the stator. And then we have the impeller. Now the impeller blades that you see here, sometimes it's referred to as the pump. And then this is the pump cover. And then we have the impeller hub or the converter hub. We often refer to it as a converter hub. And that is the component that is, a lot of times you see this in the front pump bushing right here as wear. And that installs into the transmission, and there's your pump gear drive at that point right there. Okay, failure modes within the converter is we have runaway heat, where the heat gets greater than what the design of the material can handle. So this is what we have. That's a piston that has been overheated. You see the burnt material. And then here's this is a Allison 540 stator cap, a phenolic stator cap. It's gotten so hot that it's actually started to blister. And then here, this is overload. So we've got different types of failure modes. One of them is the runaway heat, and this overload one is where the design of the converter is not sufficient for the amount of torque that's going through it, or the clamping force that's going through it. And you see here the lining has come apart. And the reason that this lining actually came off, it fragmented. It didn't fragment because of heat, it fragmented because of overload. So in the clutch paper material, there's a bonding to it. And once the overload of torque, or the torque coming in, is greater than what the bonding material is in the paper, it starts to let loose. So this is a failure because the glue bonding actually fractures. And that's because the torque load is higher than what it was designed for. So on the overloading portion of it, you can have overloading. We just talked about the paper material being fatigued from over torque. And you can also have overloading as far as the pressure. Now this one has pressure overloading from torque of the engine, but also pressure loading because of the deflection of the converter cover. So what you see right here, this dark spot, that is the torque overload from the engine. It twists the pad in the direction of rotation, and then it actually lifts the leading side and depresses the trailing side. And what happens then when the converter clutch tries to lock up, we'll show you here in physical parts in a minute, is that the clutch material right here is actually skipping over the top and not sealing in this portion of the torque converter right here. So we'll show you that in hard part. Okay, so we also have deflection of parts by overpressurization, and that's what we've got going on right here. This is a test that Ed Lee sent me photographs of this. So what it shows you is that as converter pressure builds up, the amount of deflection in the cover increases. So we've got dial indicators around the outside. As charge pressure increases, so does the diameter of the converter. It balloons forward towards the crankshaft. Excessive pressure distorts the torque converter clutch piston that you see here. And this is a good picture because you see the dark line, this radial dark line around the inside of it. That comes from the pressure actually deforming the piston. So originally, this is the outside of the piston here. Pressure initially, when it's a new converter, will clamp the lining on the outside, and then as the pressure increases, it flattens out and the whole lining contacts the cover. We see by the dark line that we have right here, what's happened is the piston is actually deflected so many times that it's deformed, and now it's actually lower on the outside than what it is here. So this contacts first, and that lining will never fully contact the cover the entire time, because once the piston takes a set, it's no longer matching the cover, and I'll show you that in physical parts here in a minute. So this is another example of when it's gone to the extreme. It starts out like this, and the longer it is overpressurized, it actually folds over backwards. And this is a 4T65E piston. You're probably familiar with years back where we had overpressurization for the converter clutch apply pressure. Eventually, you can see here it starts to eat away at the lining on the inside, and it keeps chewing it off from the inside until the lining is so thin that there's nothing left of it. So these are the various stages of over excessive apply pressure. The other thing that happens is as apply pressure keeps increasing and the blades inside the turbine, they open up the windows. That's what these are called right here, these openings. I'll show you that in hard parts in a few minutes. The newer converters now are all furnace brazed, so I'll show you the windows in the physical parts. Okay, so low apply pressure, you see this illustration right here. In the previous one, let me just back up here again. This is excessive apply pressure, where the piston is deformed and now it's clamping on the inside. And this is low apply pressure. So here you can see the burnt mark on the outside. That is an indication that the converter didn't have enough apply pressure when it into lockup. So it continually rode on the outside and it burned the lining out here. And the pressure that's supposed to build up and fold this piston flat, it never obtained it, never got to that point. So this converter in drivability would basically be a runaway pressure. It would have a high slip rate and probably wouldn't lock up. It starts setting 740 codes, etc. And we're going to be talking now about this low apply pressure causes the fins on the converter, they will actually start to fold over, and this is a picture of that, where if the converter is not charged up properly, it cavitates in the middle, right in the middle, right around the stator. And as it cavitates, it's called an implosion. The low pressure spot builds up, you might say, small little tiny bubbles, and as the pressure increases, those bubbles collapse. And as the bubbles collapse, it starts to eat out the edges of the impeller blades and turbine blades right in through here. And as that increases, it eventually starts to tear these two blades apart, and they end up going into the radiator like we talked about before. So that's a low converter charge issue. And another low converter charge issue that you run into is, this happens to be a Ford 6R60, and you see the cutouts. These are oil flow grooves in the lining. What can happen with that is the lining starts to flake off, and the oil has more leakage, loss past it, than what the applied pressure can compensate for. So you will never get to a good charge pressure in a two-path if all the lining starts to flake off through here. Okay, so we are going to move into variations in torque converters and some of the dynamics and terminology in that. Basically, there's components that are the same between these converters as, for housings and all that type of thing. There's basically two oil paths and oil flows that we will be talking about. We went through some of those on the PowerPoint, but I'm going to just do a once over on the physical hard parts. So this is a 6F50 converter, and these are, Sean and I were talking about it here before, these are what they call them pancake style or high efficiency converters. Notice how thin this converter is. I'm going to slide in the next progression, and this is a GM 6L90. So look at the size capacity difference. I mean, if you're talking quarts of fluid, you're probably talking, what, 8 on this one and 3 to 3.5 on this one. So these have to be very efficient to get the same amount of work done, but generally that torque converter is put behind a small engine, and it is also high multiple gear ranges. So you're talking 6-speed here, and you're talking probably a 6-speed at this point, but small engine, and these converters now are used up to 9 speeds. We have one here from a ZF9, and they're approximately the same size. They just have to be more efficient. So they're turning them into real shallow. This is the impeller side. So the impeller is, the converter rebuilders call it a pump, but technically if you look at a lot of SIU information and design information, they call it an impeller. So basically it does exactly what it says. The converter is charged with a fluid pressure, and that charge takes place in the valve body. The source is the pump, of course, pressure regulator valve. From there goes to converter regulator valves, and it charges this. Generally, charge pressure is somewhere in the neighborhood, minimum at 50, 55 at an idle, and at maximum it usually runs somewhere around 80 to 110 psi. And the reason that you have charge pressure is that it forces all the air out. So when you fire this thing up initially, maybe overnight when it was standing there still, some of the fluid drained out through clearances, pump bushing. So we're talking pump impeller bushing right here. So clearance between that and the pump itself will allow the fluid to drain down through the back of the front seal back into the sump of the pan. It can also drain down through pump gears, through pressure regulator valve, manual valve, that type of thing. So when you first fire this thing up in the morning, you could have a bit of a drain down, and when you fire it up, that fluid, the charge pressure has to push that air out. What people don't realize is until you put a flow meter on, that when these converters are not charged up properly, we're talking about charge pressure here. So typically you run, like I said, 50 to 80 to 100 psi of charge. When this isn't filled up completely, the center of the converter has a low spot, low pressure spot. It's called cavitation. Well, basically, as you're pushing that air out, and now you're forcing the vehicle to drive down the road. For example, 62 TE, 41 TE, 47, 46 is all the Chrysler front-wheel drive and rear-wheel drive. Because I've done so much with the flow meter on this, you can actually drive down the road for 3 to 5 miles and still not have good, consistent cooler flow. It'll just be a little bit, and then it picks up, and then it's a spurt and a curve. And you don't realize it, but you're actually starting to cavitate bushings and score bushings at that point. So it's really important to fire these things up, make sure the converter is charged up, and that you got good cooler flow before you start taking off down the road. So,
well, I hope they don't do that in the 4L60E, because within 50 RPM of my engine starting, I'm usually moving.
Yeah, and the thing is that you guys are in the warm zone, I think, here already. Yeah. I mean, we're creeping up there, and when you start to add that cold weather perspective in addition to a poor converter charge, it just accelerates everything. Yeah. So, and that's why up north I suggest everybody goes to synthetic fluid, because it makes all the difference in the world. Charging, hydraulic stability, and also cooler flow when it's cold. So, okay. So back to, that's charge pressure is what initially fills up the converter. So another pressure that we talk about is is release pressure. So release pressure, okay, so inside the transmission itself, I don't know if you can see the feed holes, but I can. It'll charge the feed holes through the pump stator or the stator support, whichever you've got. You know, a lot of these transmissions now are offset pumps and all that kind of stuff. But so to digress here again, bushing clearance is extremely critical when you start talking about this, because if you have a worn bushing on one end of the stator support, you're losing fluid. That's going to be the release. The release oil is the oil that comes out the end of the turbine shaft, okay, and it pushes the clutch piston off and holds it off of the cover. Okay, so the clearance, it's called release clearance. Release clearance is between the clutch and the cover. So let me just pull this off here. So now you have an idea of where the source of that oil comes from. But if you look at this is the turbine. The piston actually floats on this. Okay, so now we have the three pieces here. Okay, so this is the turbine. You notice the O-ring on that? Okay, that O-ring is the seal that goes right here, and this piston then, if you can see it moving up and down, this piston actually floats on this turbine hub, which is the part in the middle. See the steel piece in the middle with the O-ring?
Mm-hmm. This whole area?
Yeah, that whole area. So what happens in these is, if you think about it, you got two masses, and this is a fairly stout, heavy piece. You've got that mass floating around the outside of the turbine, and the only thing that is really centering this mass of spring and components is just that small little hub in the middle. Okay, eventually what happens is it starts taking out that surface.
Oblonging it, or like egg shaping, or just completely?
It can do all three. It can actually, generally what you start to see is this O-ring groove. It leaves an imprint right in that surface there. And so then what ends up happening is this piston starts to catch on that. So instead of being free travel fore and aft, you know, into the cover to apply, it starts to stick on that, and it also will start to leak. One of the issues, the failure modes of this type of converter, this is a two-path converter again now, is that the O-ring here, the O-ring can actually downsize. It shrinks. That was one of the problems with the Hondas. Years back, you're familiar with that. They went with a larger O-ring and a better seal there. Another issue is, you can see there's a metal-clad lip seal there. Okay, so part of the issue is, if we go back to your shaft, is, you know, when a guy's at the bench and he's taking the converter and he's shoving it onto the turbine shaft?
Yeah.
Okay, if you're not real careful with that, you know what you're going to be doing.
You can pop that out, that seal, or you can score it, or
pop it out, score it, or damage it.
Is that why they have you install, in the service manual, they always talk about making sure on the bench the transmissions face up, and then you drop the converter down with those handles, as opposed to sliding it in from the side.
Right.
Is that why they want you to do that?
Good point, because sliding it in from the side, what you're doing, you're putting all the weight on one side of this. And if this turbine, so see, this is free floating up until the time that it gets onto the shaft. Okay, so this can actually, it can move around in there, and it can move in the cover too.
Swing around.
Yeah, so you can see it can move that way.
Okay.
So if you're loading it sideways, you've got all of these components that are off center. Okay, if you're loading it this way and now it's on center, now you can set it on. Okay,
Right.
The other part, and I mentioned that in the PowerPoint, is when you're taking that top half, the bell side of the case, and you drop it down into the I call it the center support, but there's a seal there that sits down here on the turbine shaft. You can do the same thing there. You can damage that one. So there's two seals that are really critical for this. Three if you count the O-ring. The one that sits here, the one that's on the center support, and that O-ring are the three main seals for the converter clutch circuit. Okay. Okay, so back to this. So release clearance is the area and the travel of this piston. We were talking about how the piston now travels on the front of the turbine. It can slide back and forth. So when it's in release, oil pressure is coming down. Let's go back to this. Okay. In release, oil is flowing out the turbine shaft, it's filling this area, and it's pushing this piston away from the cover, so it's released. Then it charges, the fluid continues to flow through the converter, filling up the rest of it, pushing the air out, and charges the rest of the converter, okay? So once you're going down the road and the speed sensors and temp and all the other requirements are met to lock up, then it's the valves in the valve body, lockup solenoid, etc., starts to reduce this oil pressure that's coming out the end of the turbine shaft. So this clutch now, because there's still is pressure within the converter, there's pressure on this side and reducing pressure on this side, this clutch starts to float onto the cover, and it gets pushed down onto the cover. Okay? When that happens, now it's in lockup. So the components are now one-to-one. Okay, so your flex plate is now driving the turbine shaft. Okay.
Now I noticed on this thing here, it's got the woven fiber, and are those designed to pass a certain amount of fluid through it? Yeah.
Yes, it is. This is what they call a woven basket weave, woven carbon material. Okay, and carbon. And I'm going to show you that here. This is, so I'm going to let you answer the question.
Me? Oh, no.
Oh, yeah. Here we go. Okay, so you want to put that in your...
Yeah, I can see it on the top.
Okay. So what's that?
Wow, 2.5 ohms, and it's dropping. About 2.1 ohms. Wow.
Okay, so what's that mean?
It's conductive.
It's a conductor, yeah. Carbon is a conductor. So the principles of carbon is that as the converter heat builds up, it dissipates that heat through the carbon and into the cover. It's a conductor, so it transfers that heat. The oil is able to flow through the lining, which also takes away heat. So part of your question was, where does that fluid end up? That fluid then ends up with the rest of the converter charge circuit. Okay, so your turbine sensors and adaptive strategy and everything, it's just monitoring the slip rate, and if it needs to, it will increase or decrease the oil that's coming down the turbine shaft to make sure that this is slipping at it, whatever calibration that it requires. Okay?
I have heard of vehicles, and I'm not really certain if the 6070 6F50 falls into that, but it might, where they run into a TCC surge hunt kind of situation, and it's because I guess the slippage is outside of the computer's adaption or programming, so it's overcorrecting. And is that, have you heard of that? And is that usually a converter issue or a valve issue or both? Or
actually, I believe it's a combination of many things. I mean, after it's been doing it for a while, some of it is fluid degradation. Some of it is the clutch lining gets glazed. Some of it's the cover distortion. And some of it is just the programming. A lot of the flashes now, you take it in, and what they end up doing is they just delay the lockup. If the lockup is occurring at such a low RPM, low pump volume, and heavy load, this clutch lining can't hold on, okay? This is another thing to digress, is that it's called the coefficient of friction or whatever. This is one of the lowest coefficient of friction.
okay.
When you get into paper, it's got one of the highest coefficient of friction, okay? So it takes a lot more pressure and clamping force to keep this guy at a low slip speed. But the carbon is actually made and designed to have a low continuous slip speed. That's why GM was using it for years back. So if you have a lower continuous slip speed on this, so I'll let you think about this one.
That's an open circuit.
Yep, so what's that mean?
It doesn't conduct the heat away that, like the woven carbon fiber would.
Yep. So paper,
Insulator.
it's an insulator, exactly. So as the heat builds up in the rest of the converter, this is an insulator. Paper, this is composition paper, which means paper fiber is ground down, and then they also use an adhesive and they glue it onto there. So wood, of course, if you think of a telephone pole or whatever, it is an insulator. So as heat is generated in the converter, it cannot transfer out between the clutch and the cover itself, so it generates heat. And eventually, if this is allowed to slip too long, and this is a Chrysler 62 TE cover. So Chrysler does things a little bit differently. Here you see this clutch, the friction material is bonded onto the piston. In this unit 62 TE, the clutch material is bonded onto the cover. But technically they are the same. I mean, I'm sure this is also a paper lining. Yep, see, there's no conductivity.
I'm surprised you don't get like extremely high resistance. You got nothing.
Yeah, and this is already burnt, you know.
Wow. Yeah.
You can see it's burnt, but it still is an insulator. So
if it's slipping, it's not going to be pulling the heat away through the friction material like it would if it was a woven carbon fiber or something that's designed. So I guess the kind of the takeaway on that is if the converter was designed to have the woven, it's not just because of its friction characteristics, it's also the way it handles its heat.
correct, right. And then if you look at this one closely, if your camera picks that up, you can see that there is actually oil grooves in this. And I have some other converters here too, but there's small oil grooves. Those oil grooves are actually intentional in there to try to keep fluid flowing across that clutch piston. So as the piston comes down, the way these pistons are designed, we'll go through this in several other converters, but technically the piston comes in at an angle. They say it's a 1 to 3 degree angle. It's a deflection angle. So if you can imagine this with my hand, so if this is a 1 to 3 degree angle, the outside of the piston comes down and contacts first. Then as the pressure, the charge pressure in the converter increases, it flattens it out, okay? So just the tip of the outside of these discs, back to the F4EAT again, or GF30s, the tip of this, if you were to run a dial indicator around it, generally these, it's higher on the outside than it is on the inside. So the outside edge comes down first, contacts the cover, and then as the pressure builds up, it folds it flat. So now you've got 100% of the lining contacting the cover, okay? Now the trick is, when these pistons get deflected, where I'm referring to there, is that once it's in lockup and this piston's pushed onto the cover, if you have more pressure pushing against this than what it was designed for, eventually it starts to distort the piston. So instead of it being tapered down, now it actually it's flipped up the other way. And we've got some of these coming up where it's actually burned on the inside. Okay? And that's because the piston is already folded back. It's tipped back instead of tipped down.
Too much pressure causes that?
Exactly right. Too much pressure has caused it. And it gets to a certain point where the piston is actually made with cycle times that it can come down and fold flat, let's say 1,000,000 cycles or whatever. And after it's been overpressurized, that cycling is completely gone as the material has just been overstressed. Okay, so back to this. Part of the clutch piston, as you can see here, this piston has damper springs on the back side of it. Okay. The damper springs, they're made so that it will dampen torque in both directions, in the drive direction and in the release or deceleration position. So these damper springs, and these are radial damper springs, you can see they go around the outside. Okay. On the ends of these, they have a pad or a stop. And what the converter rebuilders are fighting is that these pads or these stops eventually crack or break off, or in some cases the springs break. And then that material goes, through the entire converter, starts to embed everywhere, and it's really difficult to clean it. A lot of that material ends up underneath all of the rivets and this damper plate, and about the only way you can get it cleaned 100% is they have to go in and grind off, cut out, or drill out all of these rivets and take the whole assembly apart and run it through ultrasonics or some special way of cleaning it out. Okay?
That sounds like a lengthy process. So are there solutions, like do you sell these whole plates with the springs and everything in it, so that way if they do go through the process of changing that out, they don't have to rebuild this, at least they can just put a better system in?
We do. I have a 62 TE I can show you here, and we do exactly that, where we have a replacement piston because the piston has come to the point of deflection where it's overstressed. So the guys will go in and they'll cut these off, the rivets off, and then they'll put a new damper assembly over the top of a new piston.
Okay.
It's a really heavy billet piston. I know one of the questions we got started with here before is if you look at this turbine, let's move this out of the way here. Look at that turbine and this turbine. There's two similarities between those. Okay, now if you look at this turbine, what's the difference between all? So this is an impeller. You see how it's the appearance, and there's a turbine, the appearance of that. Here's a turbine, and here's a pump or impeller. See?
Furnace brazing versus just crimps.
Right. Yep, that's what I'm looking for. That's what I'm leading into.
Yeah.
Yeah. So the reason this furnace brazing, basically what that is, it's a powdered bronze metallic combination. They pass it through a furnace, and it actually melts it down. And then like if you're soldering pipe, how the solder always sucks to the mating areas, and that's what happens here. It fills these up. So it has two purposes. For one, it makes it very strong, and for number two is it closes up what they call the windows. So when you have a turbine like this, let me get the piston off the front. So if you look at it really close, and maybe if you set it up just right, you might even be able to see light through it.
I saw it just from my angle.
Okay, you can see light from different angles, and there's the windows. There's windows and openings between all the blades.
Yeah, if this was a glass of water, you wouldn't get a sip out of it before it spilled out everywhere.
Yeah.
And this is stock, right?
That is a stock. The earlier years, if we went through some of the 3-speed, 4-speeds, none of them were furnace brazed, but they've found out now when you get into these low-profile, high-torque converters that they need as much stiffness and make sure that you don't lose your it's called crosstalk, basically. It blows right through the windows. So instead of doing work, it ends up on the cover side of the converter, and it's just wasted, you might say. It can't do the work that it's designed to do. So the other thing that happens, it makes it very rigid when they furnace braze these. So what the converter rebuilders are up against is that all these components, they generally 20 to 30 thousandths clearance or whatever, and they're running at high speed at different rotation. They can't have any run out. Like you think of a bent rim going down the road and it wanders. If that happens with this, what eventually occurs is that the two components start to contact each other, and then you've got metal going through the whole unit. So furnace brazing stiffens everything up, but it also makes everything run true so that you don't have that run out and that deflection from the mating parts.
So why, like every once in a while you'll see where they've been TIG welded, somebody will go in and they'll TIG weld them. That's just to stiffen it? Obviously they're not going to address the windows that you're talking about. Because this is something that a rebuilder could do, right? If they had the equipment, if they had the furnace. Correct,
right? There are companies. I'm not aware of any actually converter rebuilder that does it in-house, but there are companies where they'll send whole pallets full of a certain turbine that they want reinforced, like say it's HD, or they add to, they'll push them back into shape. they might TIG weld them, and then they'll send them to a furnace braiser, and then they'll stiffen them up, okay? So they'll do it that way. But in the TIG welding basically is to get the turbine back into a good parallel, non-run-out position, okay? When after these have been running for a while and they're working really hard, it starts to push on the blades, and the blades then move and open up the windows even further. And I didn't bring one with me here today, but we did a lot of work with Allison 540s, and some of these really high torque vehicles, they'll actually open up the windows, and you can take this and just shake it like a rattlestick or whatever. You know what I mean? They just shake. Well, as that occurs, then the clearance between the two components opens up, and there gets to be more distance between the impeller blades and the turbine blades. Again, they call it wash. It's just washing right around the outside, and it's not efficient anymore. Okay, so your work is lost. Just it actually increases the temperature. Temperature builds up, and that was in the PowerPoint there. We showed you that there was a black phenolic that's out of a 540 Allison, and it just actually blistered the plastic on the outside from the heat. And you know, they're putting those 540s in heavy-duty dump trucks and all that kind of stuff, and the stall ratio on those is so extreme. You know, the engines are screaming and the transmission's not even hardly moving. So there's so much heat generated in there. Okay, so now we're going to start to get into the converters themselves. We're going to start out with the popular 6L90. There's two different types of 6L90s, but there's a JMBX and another one, GMBX. And this one we have right here is called a captive clutch type of converter. So I'll show you the parts here on the bench in a couple of minutes, but the fluid enters, this is a two-path converter, fluid enters down the turbine shaft, like you see here, through the spline area. Fluid is going to go between the damper, and it comes up here and releases the clutch. So this is the clutch lining. Clutch lining is a friction seal right here, and as the fluid flows past that lining, it holds the lining off the cover, and then the fluid turns into a charge pressure and fills the rest of the converter, and it eventually exits back out between the hub and the stator. Here's an illustration of the different converter designs. Here we've got the 6L45. This is a smaller converter with a floating piston. I'll show you those hard parts here in a minute. And then this is the captive clutch design, which is a really complex unit with holding springs and multi-plate clutch in it. 4L60 and 6L80, we'll show you those on the bench here in a couple minutes. The difference is in the damper. The 4L60, the JMBX that I mentioned before, you can see that the damper is actually between the turbine and the piston. And then we've got the JMBX here, and that's the one that has the damper, which is between the cover and the piston. And these codes that I'm mentioning here are right next to the pilot. See that code? There's an exploded view on both of them, and they're right next to the pilot. Okay, 6L90 carbon clutch failure. I'll show you some pictures here on the bench in a minute. The biggest issue with this is the distortion of the cover. And the cover, as I showed you before, with the pads being distorted, the lining does not come down flat on the cover, and it starts to chew away the lining. As you can see here, here's an imprint from where the lining was skipping over the top of the pad. Another problem that these have is the windows break. Here's the damper springs that you can see right here. On the end of the damper springs, when they come to compression, they start to crack the windows out here. And I'll show you that in hard parts in a minute. Okay, here's the cover deflection that I was showing you. You see the little high spots here. You can see there's some of the high spots right here, and that'll show you in the hard parts. Cover distortion is from torque of the engine plus overpressure and the cover not being thick enough. Here's a cracked piston that used to be familiar in the 4L80s. It's also happening in some of the 4L60s. And this is from pressure and then also from the clamping force on the outside of the piston. So the lining comes down. You can see the darker portion right here. The lining contacts that area first, and as the pressure increases, the piston folds down, shuts off all the flow past this lining. This is a carbon lining, so we'll flow some through it. And then once that lining is compressed, then as the pressure increases, it keeps on pushing on the piston, and at a certain point, then they crack, and that's what you see right there. And of course, once they crack, then the apply pressure is exhausted out, and it no longer applies properly. Here you can see a couple of examples of how the lining comes off. This is when you see the bottom of the transmission pan is just loaded with material. And here I've got a picture, another picture of the damper being cracked at the end of the damper springs. And then what ends up happening is as you have all this material that is coming off of your pistons, it ends up going through, circulating through the rest of the transmission. And here you can see it starts to burn off and starts to fragment the stator cap itself and takes the material out. So when you have aluminum inside the transmission and there's no aluminum failure, it's generally coming from the stator. That's the main aluminum component within the torque converter.
Got a 6L90, I see.
We do,
You know how I know that?
because it says 6L90.
It says it right there.
Okay, so I don't know how good your eyesight is, but can you see what it says right there?
JMBX.
JMBX, right. So 6L90, there's a JMBX, and then there's another TMBX. And the JMBX looks like this internally, basically. So the big differences between the two of them are the type of clutch. So this is a two-path converter. And like we explained here before, release pressure flows down through the turbine shaft, lifts the piston off the cover, and once the piston is lifted off the cover, fluid flows around the inside, charges the converter, and goes off to the cooler. Okay? When it goes into lockup, the piston is floated down onto the cover, release pressure is decreased, and apply pressure is increased. And the apply pressure in a GM is controlled by the converter regulator valve on the 4L60Es, and also has a converter regulator valve in the 6L90s. And that material is in the PowerPoint too, so we'll go back to that. So back to this JMBX. I'll just open this up so you can see the rest of the material in this. You can see this is not a furnace brazed converter. Okay, this is just a open window type converter. Here's the stator. Okay, and then this is the pump impeller. Okay, quite different and much bigger than that little 6F50 we talked about before. Okay, those little pancake, small, thin profile converters are completely different than these guys. So
They don't have to worry about squeezing them in because of transaxle. They want the transmission to be as short as possible, whereas a rear-wheel drive, I guess they're not as concerned with, huh?
Yep, right. We have more linear length on a rear-wheel drive than you do compacted between those axles, right? We'll leave that the way it is. Okay, so the big issue that the converter rebuilders are dealing with, and then of course the guys in the shops, is the converter failure. And it starts out as the the initial shutter, or it's got kind of a chatter on 1, 2, 2, 3 or whatever, and eventually that chatter leads back to the whole clutch degrading. So we talked about this a minute ago, but basically what's happening is initially this piston had an angle on it, which would be they called it a 1 to 3 degree angle, where it came down and contacted the outside of the cover first. Then as the pressure built up, the lining flattens out and mates with the cover surface. Well, as these pressure keeps increasing, and that pressure increases because the hydraulics wear out, deteriorate in the valve body, the piston starts to go over center. So I don't know if you can tell this one or not, but it's been pushed this way towards the cover, and it is no longer has a proper angle to it anymore.
Yeah. Huh.
Okay. So that is one of the issues with the 6L90 is the covers get to a point where once the lining is gone, it's taken so much material off of it that the converter rebuilders don't have anything to deal with. They can't cut it down because it gets too thin and just distorts even more so. The other part is the pistons. So Sonnax makes both the pistons and the covers. And we also have damper assemblies. So before I walk over that, just to let you know what happens with the dampers is when this goes into lockup, this damper is, it's loading in the direction of engine load, and then on deceleration, if the converter clutch does not release. And if you think about it, without a lining in there, and these two halves are metal to metal, it's pretty hard for the release and apply timing to be correct, So when it's in the driving position, the damper is loaded one way. When it's in decel, if the converter clutch is still applied, it swings back around the other way, and now it's loaded in the opposite direction. And the rear wheels are basically driving this clutch into the engine. So, and to talk about that, if you have, like say the 6L90s in tow haul mode, and you've got a heavy trailer on the back, that's exactly what's going on with these things. I mean, they're driving it both directions, and that lining, in this JMBX, it has a single friction lining, and it just, really works them hard, tears them apart. So back to the damper, what happens in the dampers is that it starts to crack these round radius windows open, and then the converter rebuilders don't have material to work with. They have to salvage another damper. So we do make this damper assembly.
So I guess, usually you see people round those holes out so you don't create a stress point that creates a crack, but it's still not good enough. It still cracks there, huh?
Yeah, it's metallurgy, design, thickness of material. The biggest thing is the thickness is just way too thin. Yeah. So we have a new damper cage, you might call it, that is actually thicker, and it's got a lot more forgiveness to it. Okay. So that's that JMBX, and this is the cover then that we made. So this is the cover in comparison to the OE. Okay, you see the material thickness?
Yeah.
Between the two?
Uh-huh.
And then if we flip it around to the other side, you see the pads?
Yeah, well, they're not welded for one. They're part of it. They're machined into it. That's nice.
Yeah. So what happens too under drive direction, part of the problem with the cover failure and the overpressurization of the piston is that when these pads are welded on and the engine is always driving it in one direction, it takes that pad and it flexes it, okay? And it flexes it enough that it starts to distort the cover at each drive pad. So now when the clutch comes down and it hits the cover and it needs to seal off, it actually just hits the high spots, and the high spots for each one of those pads, and it starts to etch away and deteriorate the lining, takes it off the top.
And really, I guess it only has to deflect just a few thousandths, really, or maybe a couple thousandths to really cause a problem.
Mm-hmm.
Have you ever measured, or is there a way to tell how much deflection actually occurred?
Well, I have not, but I'm sure that there's a point, and we could guess at it. Yeah. There's not much forgiveness in the lining, and before we put the ohm meter on the lining, that's one thing about carbon linings versus paper. If we back up here, paper is more forgiveness and more flexibility, and these carbon linings are actually very brittle. Okay, they'll actually fragment, and they don't take a lot of impact, and that impact will actually start to nibble the corners off of it. So, and then that's the lining that is used in these is the carbon fiber lining. So how much of the speed bumps it'll take before it breaks up, I mean, I'd be guessing. I can't really say, but it's not that much, okay? Okay, Sean, so another thing we should cover here is on the turbine. Get a close-up of that. You see the spline condition? This is called the turbine hub, okay? It's riveted into the turbine. And these can wear in different ways. We talked before on the 6F50 of how that O-ring, this actually has a Teflon seal in the GM units, but this can actually wear into the piston, and the splines wear then into the drive hub. Okay, I'll hold that, and then so so this area right here, that is the contact area for that groove, for the sealing ring. Okay.
See a shiny spot on it.
Right, and that will wear out. So the converter rebuilders, if this is worn out, they have to turn this and press in a sleeve. And if the turbine hub itself wears out, then there are replacement. Sonnax makes a replacement turbine hub. So that is one of the conditions. Is actually this area will round down because of it's been pounding. The piston will cycle around the outside of this, and it starts to chew the inside of the piston out. So that is actually, the spline on this turbine is actually pretty good.
Yeah, that wasn't chewed up like the one.
Yep. Okay, so now we'll show you another example. You see the splines on this one?
I see half of them.
Yeah,
The other half are worn out.
that's how thin they get. So they'll wear out, and they have to replace the turbine hub. And that's,
Will they strip out? Have you seen them where they actually lose them all?
yep. And usually, if it takes this and it runs long enough, then it'll take the mating spline out of the damper.
Yeah, so this one's in good shape.
So these actually go together like that, but it'll take the spline out. Okay. Another type of 6L90 is the captive clutch. The one we just had here a minute ago. This is a single clutch, that JMBX. Okay. Then we have another type which is a captive clutch, and this one is really giving the converter rebuilders a fit, and actually it's giving vehicle owners a fit too, because it has some unique failures that lead to a lot of contamination. Okay, the linings come off. You can see the lining starting to degrade here. Captive clutch has got a multi-plate, so there was a friction on both sides of this at one time.
Not on that side anymore.
Not on this side anymore. Nope. There's part of it left on that side.
Yeah, you can tell it's a woven carbon.
Yep. Okay, so that lived here, and then you had a backing plate right here. Okay, this was riveted into these spring retainers. If you can get a shot of that. So before this was taken apart, and again, hats off to Jeff Stuck at Certified. He sent me these parts, cleaned them up for us, and sent them off to us. But that was riveted. So what they have to do as converter remanufacturers is go in and clip off all these rivets and then take them apart. Okay.
So that didn't rip out. He did that just so he can get to the piston to inspect it.
Correct. But some of them will rip out. Some of them actually rip the rivets off of the covers here, or they off of the disc. And the problem is of course salvage of the components. You can see here this clutch backing plate is pretty well gone, and this one is pretty well gone. See how it's deflected? See, it's distorted?
Yep.
Okay. And then you get to the cover.
Well, here's
So-
a question for you.
Yep.
Flip that around so I can see. These are only pulling the plate. Do they ever run into issues with the engine braking? Do they ever distort them the other direction?
Yeah, I've seen them break off. Actually, the 6R140s, they snap them off right here at the edge, where it stops. Because you think of it, okay, so like an accordion, as an accordion fold in paper or whatever, if you figure it that way. So you fold it, you bring it back, you fold it, you bring it back, and eventually the paper gets really thin. Well, that's what happens with some of these. This is all spring steel, but eventually it gets fatigued, and then they'll start snapping off. Sometimes they snap off at the rivet down here, and sometimes they snap off at the rivet at the top. So another thing that we were going to cover that makes this difficult is if you look at this cover from the back side, you see these are extruded rivets, you might say. It basically is pressed from the back side, and that extrusion or that piece comes up to the top, and then they rivet, they stamp the top of it, turn it into a rivet.
So that was built into the cover. They placed the piece down, they placed these straps down, and then they let the metal from the cover become the rivet.
Yep. Mm-hmm.
That's not good for rebuilders.
Good point. That's not good for the converter rebuilders, right? So that's what they have to deal with. And a lot of the cores are coming in like this now. I mean, with the same type of failure. So the material that they have left to rebuild from is getting less and less.
Let's say that clutch wasn't destroyed and they're rebuilding this. They can probably fix the piston or, replace the lining on the piston. Is it difficult for the rebuilders to go in and re-rivet these things down? Because is that what they'll have to do? They'll have to reuse everything because if they have a rebuildable core, they can't address this part right here at all, can they?
That's correct, right?
Okay, without getting any cover.
Right. Well, some of them, there's some other converters that over the years have used this same type of extrusion. And what they'll do at that point is, let's say, for example, these are busted off and there's nothing to work with. They'll go in there and they actually drill a hole completely through, and then they put a rivet in it, and then they weld it. They weld it.
Seal it, basically.
Correct. Yep. From distortion and fatigue and all this kind of stuff, there isn't much left for the guys to work with. The other issue is, you were talking about the linings, and we didn't cover that very much, but there's actually they'll strip the linings off of this, either again with CNC or bead blasting or on a lathe or whatever. But there isn't much to work with as far as the disc anymore because they have to clean it up. So then they put it into a bonding. Bonding device is, what's a good way to explain it? You got a high temperature fixture comes down over the top of it, and they've got a floating lining piece of paper. In this case, the guys bond back off this woven lining that we actually source it from the original supplier. That lining is bonded back on there, and then they put it back in. Part of the problem, though, is that after they've machined this and the cover, and they have to remachine this, it's called the clutch clearance or whatever. So the clutch has got a specific amount of travel. That better flip it over, but it has the clutch piston itself has to travel up, and that's what these springs are for, is to stop the thing from just blowing off into the turbine. This holds it in direction, but it also holds it in position at traveling height. So as they keep removing material, all of this to clean this up, now you've got excess travel, and all of that, of course, changes the timing for clutch apply and release and the whole thing, because the computer has to hydraulically compensate for it, which is tough. Yeah, so this is the repair for the captive clutch. That is the infamous captive clutch that has a high failure rate. So what we've come up with, this is a Sonnax product. We have a heavy-duty billet cover. Okay, you can see the drive lugs are not going to flex. A lot of material for the guys to work with.
Being billet, they can make the back and the sides, they can make different thicknesses wherever they want. So this back section, I can feel right there, is thicker than this section is machined down thinner, probably so you can use the front half or the rear half of the converter. It's nice. Mm-hmm.
Yeah, it's nice and it's heavy. Yeah, it's got some heat dissipation to it too. At Sonnax, what we did with this updated TMBX, this is a multi-plate. Okay, so we actually bonded the OE woven carbon lining to these plates. So now you've got a third again of friction material. Okay, so we stack that up, and then this guy is going to stack up like that. Okay, so that saves you the process of trying to rebuild that. Okay.
All right. How long has this been out there?
Oh, not that long. Maybe I think we released it maybe within the last month.
Oh,
it's a fairly new part. Oh. Yeah, but I can tell you they're just sell them, you know, like crazy because
Now, did you say you had this in your truck? Or do
no,
you have
no,
the original converter?
I have the original
Okay.
converter. I'm sure I've got this converter in my truck, and I can actually run through that. So I don't pull that much. I've got a 9.5 foot slide-in truck camper, and so you load that down. It might be 2,800, 3,000 pounds, and then I've got a 22 foot flatbed that I put two UTVs on it. So the combined weight, you're probably around, might be 8,000, 10,000 pounds, and it can be working at that point, and I can push it hard enough where I can bring up the slip rate on it. Okay, so the cooler flow. So this is an example of 6L80, 6L90. So what you can do for diagnostics is you can use a flow meter. The flow meter actually tells you the amount of flow that's going into the converter when it's in release mode. When it goes into the apply mode is when the piston is clamped onto the cover. So release mode, the fluid is entering the converter, and I'll show you that here in a couple minutes. The fluid is entering the converter, it's holding the piston off the cover, it's flowing through the converter and flowing out. So that's unrestricted. There is no restriction between the lining and the cover. And when it goes into lockup, here you can see right here, there's an increase in the apply. See that rise? The reason that happens, I'll show you in some of the oil schematics, is that the apply pressure now has pushed the lining onto the cover. The fluid is now directed into the converter, and that's only a clamping force. That's not flow. So the rest of the flow actually goes external to the radiator and to the cooler. So the flow actually picks up when it goes into lockup. Okay, so we're going to go into the control for the 6L45, 6L90. This is the pump assembly, 6L45, 6L90. As you can see, we have the TCC control valve, and I made a note here on this side. Make sure you pull those apart every time and clean them out, because there is a tendency for those to stick, and when that sticks, you will not have any lockup. It'll either kill the engine at an idle, or it won't have any lockup at all. The other item we have here is line pressure relief. That is not affecting the converter, but it affects line pressure overall. So if that's dirty or contaminated, it usually sticks open, then you'll have low line pressure. If you have low line pressure, you're going to have low converter clutch apply. Converter feed limit, this is not on the apply side. Converter feed limit is on the release side of the pressure. So its main function is when you put the transmission into reverse, that your line pressure, high reverse pressure, let's say you're at 250 to 350 pounds at the maximum, whatever it might be, this limits that. Once it goes into lockup, it's the converter regulator valve and the valve body that takes over, and I'll show you that on an oil circuit here in a minute. So the main function of this is controls maximum converter charge pressure. Okay, pressure regulator valve, 6L90, 6L45 are known to wear, the actual valve itself wears out right within the circle here. And the bore that it rides in this is the end of it. This orifice feeds the end of that valve. And what's ironic is that the anodizing and the aluminum valve actually wear out before the casting. And the reason that happens is because there's a high content of silicon. It is a very hard aluminum material. So that silica material actually wears the aluminum casting, the anodization, I should say, off of the valve rather than the aluminum of the pump wearing out, which is opposite basically of what happens in the valve body. The valve bodies are relatively soft, and the anodizing on the valve remains, and it wears the aluminum valve body out, which is, like I said, opposite of what happens in the pump. Okay, so what we've done here is we've just identified the valves on 6L80 and 6L90 that control the lockup feel. And for shift feel, compensator feed, that mainly controls the clutch release pistons and the back pressure that allows the pistons to be in a steady state. Steady state is where a piston is brought right up to the edge of the clutch. It's not fully applied and it doesn't fully release. So in the earlier days, we had the clutch release springs, and they would push the piston all the way back, and you'd have clutch clearance. Well, with compensator feed, what it does is it keeps that piston right up to the edge so that it doesn't, your time delay or clutch overlap is much less. The other ones that we have circled here, these actually do control converter clutch applier. This is a TCC regulator valve that we have right here. And these two bores, this one and the one on the bottom, actuator feed, are really important for both line pressure and also for converter clutch apply. So if you're getting into a valve body and if you're doing visual inspection or vacuum inspection, these are the two to check first. This one and actuator feed. So I would check actuator feed first, and then I would check that one second, especially if you have a lockup issue. So in a previous screen, we noted how the TCC control valve, the converter clutch control valve, has a tendency to stick inside the pump. And this is just a quick check. If you have a no lockup situation, you can pull the valve body off and you can actually air check the pump. And thanks, Sean. You can air check the pump right here. So when you air check it right here, you can hear the TCC control valve stroke in both directions. So you give it 30 to 40 PSI, whatever, and it'll click on and click off. If you don't hear that valve stroke, you will not have lockup. Okay, another part of the pump that's often overlooked, this is a known big problem, is the pivot pins. So if I back up here a couple slides, when I was talking about the pump pressure regulator valve, the pressure regulator valve, as it wears out on this end, this is the oil pressure that reduces line pressure. This orifice that you see right here is the reduction for pressure for the PR valve. When it pushes the PR valve this way, it lessens the pressure, and it also changes the slide pressure, which is decreased pressure. Okay? Decreased pressure comes off of that spool right there. Now, the containment for decreased pressure is this pivot pin on this end of the pump slide, and then the wiper is the other end that you can see right here. There's a black rubber expander and the Teflon ring. So the oil that comes in between that wiper and this pivot pin on this side is decreased pressure, and that is actually the stabilization for the whole pump slide and rotor. And what happens in 4L60s, 6L90s, and that is that if you get an unstable pressure regulator valve that I showed you here before, if that PR valve gets worn or unstable, it takes this slide and it bounces. It's real erratic. It starts to set up an oscillation in here. And as it does that, it can crack the drive lugs off, which I believe this one is cracked right here. And it'll crack both of them out, and it'll also break out the inside of the rotor. So it happens from oscillation, but it also happens when it's heavy acceleration driving down the road, and then you let off, so you heavy acceleration, high line pressure, you let off on the accelerator, and now the pump slide goes the other direction, and when it does that, it has a tendency to wrap up inside the drive lugs, and it actually breaks the inner pump drive off. So when you're taking this pump apart, inspect the pivot pin, make sure that the pocket where that pivot pin lives in this housing is tight, that fluid cannot drain or leak past it, and then the same thing with the wiper on the other side. Okay, so we've talked about some two-path, and we'll show you more of that on the bench here in a couple minutes. And now we're getting into the three-path. Now a three-path, what's different about this is you have clutch apply pressure. It physically has another clutch in the front of the converter, and we'll show you that on the bench. And it's a multi-plate clutch here at the top. And so the clutch apply pressure transfers down the input shaft, flows out, and applies this piston right here. So there's two separate oil circuits that do circulation through the converter and keep it charged up, and one circuit that's isolated independently just for the clutch apply. Now the big thing, the differential between the 2-circuit and the 3-circuit, 3-path, 2-path, is the diagnostic procedure. Now, one of the biggest errors or problems with a 3-path converter is that if this circuit, the rest of the converter charge, relatively has 70 to, let's say, 100 psi. When this circuit, which is the converter clutch apply, is supposed to have 0, if you have any leakage between the charge circuit and the apply circuit, the oil pressure will come into the path right through here, through the seals we'll show you on the bench. And as it pressurizes under centrifugal force, it brings that pressure out to the outside, lifts the piston, and starts to semi-apply the clutch up here. So it actually charges from high pressure to low pressure when it's not even supposed to be locked up. So cross leaks within a 3-path are the detriment to that torque converter. And this is a picture of the damper assembly. Here you can see this is a really aggressive damper. This is 8HP70. And here you can see the converter clutch right here. This is the piston. And this is the center that I was showing you here before. This is the isolation and separation. So the turbine shaft will sit here. This is a seal on the turbine shaft. And then on the OD between the piston and the turbine, there's a Teflon ring right here. If either one of those leaks, the converter charge pressure enters the converter clutch apply circuit and starts to bring the piston out, and you'll have premature lockup. Usually what the event is at an idle, you'll start to feel the idle RPM surge up and down as this oil pressure enters into the converter clutch apply circuit. We've got a picture here of the splines on the front of the ZF8s and 8HP4570, which is the Chrysler designation, just to give you an idea of, so there's 3 different splines within this turbine shaft, and so what that means, and I'll show you on the converter hub, is that it has splines on the ID and splines on the OD, and it changes basically the cost of the turbine hub, impeller hub, and also the flow path inside the converter. This is the ZF8. I've got the circuits identified here. This is ZF8 valve body as far as this is a TCC clutch apply circuit. And this is the charge circuit. Those are the 2 paths. You can use those to match up in the case. Or if you're trying to trace the circuit back, like say you've got some damage on top of the valve body, this is another thing to keep an eye on is this is the Gen 2 that uses the neutral start system. When you see the valve body casting that looks like this, if you have any damage on this at all, you can get cross leaks between those paths, and it creates a lockup issue, converter clutch apply, the crowding you call it at an idle. And these are the valves in the ZF8 that control lockup. This is the main pressure regulator valve, and then we've got the TCC control and the TCC limit. So again, if you have lockup issues, these are the 3 to check inside the valve body first. And here's the lockup solenoid right here. I got that identified. And this is PR valve, and some information on this is there's multiple diameters for these. This is the reduction sleeve actually. This is pressure regulation. And then there's different diameters in the PR valves for all of the ZF8s, the ZF6s. It's very confusing because they change this differential in ratio depending on the vehicle application. So be very careful as far as trying to swap parts in the pressure regulator valve or even swapping valve bodies. The main differential is going to be that right there, the diameters on the pressure regulator valve. So in this slide, we want to talk about the control circuits for the TCC. And here you can see we've got probably one of the biggest issues for all valve bodies. The ZF8 is included, is a regulated solenoid feed. So the general motors that we've been familiar with for years had the actuator feed system that would always wear out. Actuator feed in GM was what fed the solenoid pressure. And here the regulated solenoid pressure is this. You can see it's from PRV, and the DR red is what their nomenclature is. But it feeds the solenoid regulated pressure. Here you can see it's coming up here at this point, coming around to the regulator valve. And then the output of the TCC solenoid, like I said, we're focusing just on torque converter clutch control. The output of the solenoid then goes from this point, and you can see these dampers. So in this circuit, the critical factors for converter clutch control and oil loss is this plug. And in our Sonnax information, if you go to our websites, we talk about all of our vacuum testing and the places in the valve bodies that are prone to wear. We also give you information on what our zip kits do and all this type. But this plug ends up getting loose. So what happens is this solenoid regulator pressure that comes in, that enters the solenoid, a lot of it will actually leak off between the plug and the casting and it vents to exhaust. So you have less pressure going to the solenoid, and you have less pressure than an output to the TCC control valves. The other issue that happens is these dampers inside the valve bodies. There's a little rubber diaphragm in the bottom of those, and those collapse. So the dampening output of the solenoid is lost, and then the torque converter clutch control valve actually cycles back and forth with the deregulation of this circuit right here. Okay. So this is the visual picture of it, and that's the TCC solenoid we just had in the oil circuit, and right here is the clip, the retainer that holds that end plug that you saw previously. I'll back up to it. Okay, there's that black plug, and there's the retainer. And here it is in visual, and so this is the retainer, and then the black plug lives right underneath that retainer, and that's the lockup solenoid. So again, these are the circuits for that control and feed the torque converter clutch. And we have vacuum testing tools. The solenoids are known to wear out in the ZF6 and also the ZF8s. There's a little pintle and a plunger and a seat that wears out eventually, and once that happens, these solenoids will not operate properly. So we have some solenoid testing tools. They're vacuum up. You hook them up to your vacuum pump, and we've got all the specifications are within the tool, but we also give you here acceptable vacuum is 20 inches, and new ones are usually around 23 to 25. So that wanted to show you some of the vacuum testing tools. Okay, here's an indication of the torque converter clutch, the ZF8. This is that 3-path converter. So if you look at the blue lines that come up here, that gives you an indication of coming off of, this is the TCC switch valve, basically is what it is. This is the on and off control valve. Here's a control pressure limit valve. This is basically just a pop-off valve. And here you can see the circuit comes up, and this blue and white hash line, that is the apply circuit right here. And then you've got the TCC charge circuit in the middle and the TC return. These two circuits, the TC charge and the TC return, are always pressurized. The TCC apply will go from 0 basically up to about 60 psi, and that one should vent to 0. Now, where the problem comes in is that if TC charge or return bleeds into the apply, it starts to hydraulically and under centrifugal force starts to apply that piston. We'll show you that here on the bench here in a couple minutes. So now as it goes into lockup, you can see the control valve is moved here. Now you can see this oil circuit for the apply is starting to be charged up. So the oil pressure ramps up at this point, and the piston starts to creep towards the converter turbine, and it compresses the clutch pack itself. These two, they change in pressure, but they don't go away. So back to using a Sonnaflow, when you have a two-path converter, you have, and it goes into lockup, you have apply pressure and release goes to 0. And you can see that in the pressure chart that we showed you before, the Sonnaflow chart. In this one, when it goes into lockup, you don't see much of a change in flow because you continually have flow going through the converter with these two circuits. Here you see the blue and the red. So diagnostics between the two of them are completely different. You will not see a major deflection in flow with a three-path converter. Okay, on the ZF8, this is a TCC regulator valve, and you can see we've got some notes here that the anodizing has been known to come off on these. Will give you a drag converter clutch. If the converter clutch doesn't release entirely, what ends up happening is you have bumpy shifts because the converter clutch is applied and you're shifting off the damper springs, and it gives you a bump on downshifts. Coast downshifts is most typical, and sometimes on the lower gears, like say 2, 3, 4 upshifts, it gets bumpy, and that's when the converter won't release properly. This is information on the ZF8 converter clutch pressure, and this is, again, all on our website, and we have various articles on this, how to test it, and this is information on what normal pressure is. And what's kind of confusing is it's PZT pressure tap, and that is not release pressure, it's converter charge pressure. Interesting enough is that ZF8, that's the only pressure tap that's on the transmission. It's the only pressure tap they use for diagnostics. And we've got that information in more detail here as we go through this. This is that PZT pressure tap. This is taken off of a vehicle. It's a 2015 Jeep Grand Cherokee. This is known good, so you can use this chart. This is also on our website. If you go in and look up Sonnaflow and diagnostics for ZF8 information, you can print it off of there. So this is known PZT pressure, and you can see that it typically doesn't go away, it just changes. So here, as an example, at 15 miles per hour, you only have about 15 psi of PZT pressure. When it's idle in reverse, here you've got about 80 to 85 psi. So it's continually changing, but it never really goes away. Okay, so here we're into the three-path converters, and this is the ZF original design, but this is actually, and it's even marked here, is out of a Dodge 8HP70 series. I was thinking originally it was Audi, but it is a Dodge. So in looking at this, one thing you'll notice is that you got to be very careful because you start to break these up. You see how distorted that is? Okay,
yeah,
that's
dropped.
Yeah, it's been dropped, or they ran over it with a truck, one or the other. This is running on your flex plate, of course, so you make sure that this stays true. Another thing that I know that converter remanufacturers, rebuilders really are frustrated with is when the guys send in ZF converters, they have really long extended pilots. So anything that has an extended pilot like that, really be careful, because once they're bent, the guys either cannot straighten them out or they got to cut them off and re-weld them. The other thing is, digressing here, is if the center of the crank pilot is worn out and this does not center, you know what's going to happen. It's going to take your front pump bushings out. So if this is damaged or worn, check the back of the crank, make sure that your pilot is good and solid and smooth in there and that it's not worn out. Okay, so now we're going to get to the inside of this. Like I said, this is a three-path converter. So it's got a clutch in the cover. It's basically a transmission low and reverse clutch reversed completely and put into the cover of the converter. Mm-hmm. So the turbine shaft comes into here and goes into this centering device, and we have this on the PowerPoint, so you can also see it there too. The turbine shaft comes in, feeds the oil pressure to the back side of this centering device, this hub, and then the clutch piston comes out like this. We're going to take the snap ring out, take the clutches out. Basically, it's just like a clutch pack. Okay, multi-plate clutch. Okay, And then in the inside, we have a piston, just like could be a low and reverse piston, forward clutch piston or whatever, and it travels from the cover forward, compressing the clutch, and that's your clutch apply. Now, like I mentioned in the other converters, the critical part is that the rest of the converter charge that's taking place in between turbine and impeller, so you have converter charge and converter out pressure, you don't want this mixing with your apply pressure. So anything up through the front pump bushings, or this little centering device here can lead to crosstalk, so which means that your 80 psi between turbine and impeller, if this is supposed to be 0, it will bleed in there, and then under centrifugal force it starts to crowd this piston, bring it up, and compresses the clutch. And when that happens, you start to get engine crowding, okay? And that is pulsation and RPM, and you can't figure out, is it an injector, is it idle, is it converter crowding or whatever, and it leads to all kinds of diagnostic issues, okay?
So is this I know you're talking about ZF right now, and there's a bunch of other 3-path converter designs. Does this same problem happen on others, or is this really known for the ZF?
No, it happens to all the 3-path. Yeah, it's a good reminder is that it doesn't matter what type of 3-path you have, that apply circuit needs to be isolated from converter in and converter out, because you think about it, fluid pressure is always going to the low side, right? The path of least resistance, which is, if this is 0 or 10 and this is 70, 80, 90, it's going to bleed into that. And when that happens, where the problem really comes in is most of the time this lockup valve that's in the valve body that we had on the screen before, the lockup valve is supposed to have exhaust holes and be able to vent anything that leaked into this. Okay, does that make sense? So if there was 5 to 10 psi that bled into this from a bad sealing ring, O-ring, or pistons, or whatever it is, turbine shaft, it should leak out at the exhaust valve, at the control valve in the valve body. But once it gets to a certain point and you can't exhaust it, the hole isn't big enough, then it starts to build up in here. Okay, so an example of that, we'll get into it on the 722.6, but that was one of them where the leakage into the piston was greater than what the exhaust was, and it would finally crowd it and start to shudder. But that question that you just asked me can happen on any 3-path converter. This has to be isolated.
Do you guys have any add-ins that you do on the ZF to make it better for rebuilders?
Basically on the ZF6 is, we showed you before on the 6R60, that's got the captive clutch. That is a 2-path converter. The ZF8 is the 3-path, and it's actually a pretty good converter. We really haven't had to go in and beef anything up. It's been really good. We do make frictions and steels for it. You know, we've got that type of clutch repair. We've got the centering device. We've got stator bearings. We've got thrust bearings, and we've also got rollers and that for the stator. But other than that, we haven't had to do too much. We always have turbine impeller hubs, and we always supply any bushings that you need for these. That's first on the list to take care of. So we're going to start with the 6R140 here. This is another 3-path converter. And again, on 3-path, you've got your apply pressure. It's going down the turbine shaft. Apply pressure exits between, there's a center here, and I'll show you that on the bench, where in this application, these centers come loose. It's actually spot welded right about there. And that spot weld comes loose, and this centering device for the piston starts to wander around the inside, and of course at that point you lose lockup overall. So the apply pressure comes up, travels through this centering device, which has the seals on it for the piston, travels around the outside, and then this is basically an entire piston assembly, just like you just have in a transmission clutch. So the point I want to catch here is, so that I don't think forget about it in the future is that any oil pressure that leaks from the converter charge circuit here and the converter release or the converter out circuit, if you have, say, the 60 to 100 psi in this area and you had 0 to 10 here, any of the seals leaking, so this would be the seals here, the cracked welds, or the seals that are separating the turbine from the pilot on the turbine shaft, the oil is going to go into that piston, and under centrifugal force it starts to come to the outside, and it's going to take that pressure, build it up here. It's going to gradually start to crowd that piston and come across and compress the clutches. So it comes to a point where it's a semi-applied state. And at an idle, when the pump volume is low, but you've got still high converter pressure here and low pressure here, it starts to crowd it, and then it starts to bring the engine RPMs up and down. So you see it in the tach, and a lot of times the diesel engines will recognize this, and they'll actually start to change fuel supply, fuel pressure, and that sort of thing. Okay, so in the 6R140, as in any three-path converter, you can take the oil circuit that charges the converter, which is right here. I've got it identified in the case. Once you pull the valve body off, you can pressurize that port, and that port then leads right directly through the pump, the sealing rings, the turbine shaft, and it comes out right here where I was showing you before. So that pressurized down the turbine shaft from the case, you're actually isolating this whole clutch circuit inside the converter, just like you would be air testing a clutch. And when you do that, you shouldn't have any cross leakage coming out any of these other ports, because if you do, that's indicating that the sealing rings and turbine shaft seals or this inside of the converter is leaking. So that'll cause your engine oscillation and crowding is what we refer to it at an idle. It also causes a condition where, because most of these converters now are locked up after it shifts to second gear, sometimes they're semi-applied in first. If the converter is crowding already when it should be released, you get bumpy and hard downshifts. So typically a converter will open up a bit on a downshift so that you're not shifting on the damper springs and everything. Well, if it's cross leaking and crowding, the shift is very bumpy because of the semi-applied or fully applied converter. Okay, so here we have the solenoids, and I identified the one that controls the converter clutch, which is this one. You see the arrow right here. I believe you're probably aware of this already, but all these solenoids are coded with a band number, and I've got that indicated here. And I just want to make a note from experience. This solenoid, which is the 1, 2, 3, 4, the SSA solenoid, we found that happens to be the most critical as far as drivability. Some of these other ones, you can be a band or two off and they will adapt okay, but the one that takes the longest and the hardest to adapt is this 1, 2, 3, 4. So if you're getting close to numbers, like say you had a band of 4 and you swapped it with a band of 5, it probably would readapt. And this 1, 2, 3, 4 is the one that's most critical and the most sensitive for shift timing. Okay, so we're going to have this 6R140 and just show you what the turbine side, from the turbine down into the cover, what this looks like, what the failure mode is. So this is the turbine. I'm going to lift it off, and it is heavy. Okay, now you see it coming up. There's the damper assembly. Damper springs are pretty aggressive, pretty big.
They don't look like they dampen much.
Yeah, well, you think about it, these like the new transmissions, they're locked up about right after second, and they probably are going to stay locked up all the way up and down, and this is heavy truck going to be using the damper springs for deceleration and engine braking. So the dampers aren't just used in one direction, they're used both ways, and towing all that weight and engine braking for a diesel has to have a pretty stout damper assembly. So that is the turbine, and that is the damper. You can see it's basically all one piece here. Okay, so as we flip this over, this is the drive lugs for the clutch. So this is the OE clutch, and this clutch now is, I'll try to pull the piston out of here. Okay, this has been cut out already. So when it's properly assembled, this is actually pushed down level with the top of the cover, and it's welded in there. Okay, so the guys at Converter Reman come in here and they cut this all off, and then this is basically it's the backing plate. Okay,
So when they open up the converter, they cut the weld out, take the impeller portion off, and then they find the weld for this?
correct.
Okay.
Yep, and then they go in there and they cut that off. Okay, so you can see the mating witness marks here from the backing plate here. Okay, and then another thing that you can see is there's these wave springs in here. Okay, you see that? There's two rivets and a wave, two rivets and a wave. And when you load that into this cover, give you a close-up of that, these are actually spread apart. So you have to push a plate in, then you got to preload it and push it to the side in order for the plate to go in. So they're not just dropped in, they're actually, there's a bottom plate, and then the top plate is torsionally pushed in, and then the leaf springs open it up, and that's what keeps the friction free.
But then, so both these plates are almost wedged into these lugs, huh? The steel plates?
Right, right, yep.
Does that keep it from rattling?
Well, that's where you're headed, and that's actually what the problem is these leaf springs break, the plates, the clutch plates themselves dig into the housing, and as that occurs, they won't float anymore, okay? And eventually what the drivability problem is, when the leaf springs break, you can get a clutch rattle because now everything is jostling back and forth, you know, like you would have the low and reverse anti-rattle spring gone out of 350.
Like the dual mass flywheels on these Fords, the old, you know, that once those things, they just rattle at idle because of torsional.
Yep,
changes.
good example. So that's what happens here. So there's two major problems is that the steels dig into the housing. You can see some witness marks here. Actually, this one looks like it's been dug into there pretty good. Here's a couple of them that are dug in.
So that's where the strap was?
The strap and also the edge of the clutch plate itself digs into the housing. This one isn't too bad.
It's like almost, because are there 3 straps?
Yeah, there is 2, 4, 6 of them, 6 straps total.
Okay.
But these, the plates, this one isn't just too bad, but the plates will actually dig right into the converter lugs, like you would see in a transmission clutch drum, and then they don't float anymore. Okay, so that's the OE setup right here, and like I said, these leaf springs are known to break. Okay, so that guy lives there. And then, like I said, this is a 3-path converter. So this piston now is applied by the turbine shaft comes down here, and the oil flows out of the turbine shaft, and it flows out underneath this. That is not supposed to be free. No. This part is technically supposed to be welded in here, and this is the reason this converter is here is, as an example, is that has actually been busted off. It's spot welded on and it broke. Okay?
So when the fluid would not apply to clutch, I guess, would it? I mean, because it would pop, did it pop this inner part out and leak past, or?
Right. Yep, you got it. There's no way this is going to have a clutch apply because now you don't have an apply circuit isolated from the converter charge and release circuit. Okay, it's all one circuit overall. But when this is working properly, then this is welded, and there's a seal around the outside of this center piece, and there's a seal on the piston. Okay, and then this piston will, as the apply pressure increases, this piston comes up and actually clamps this clutch together, loading it against the backing plate.
It's just a lack of penetration on their weld, I guess, because there's really, other than hydraulic force on the back side of this, there's no, it's not like engine torque or anything's traveling through this. It's just trying to isolate the pressure behind it. So that broke off just because the weld never got around, and I guess, am I right?
Yeah, I would say that's probably it. It's the weld penetration, but also if you think about it, this piston is actually centering off of this, right? And you got a turbine shaft that is being centered off of a stator support.
Right.
And this pretty heavy converter,
Yeah.
right? So this whole converter and assembly basically is being centered off of that bearing. All the mass on the inside, the turbine, the stator and all that kind of stuff is being centered off. So I could just foresee that having some, you know, torsional twist to it, and eventually it looks like she just broke off, came loose. So another is, I see this has a marking on it. See the piston, once this comes off, then the piston is pretty much floating freely around on the inside. And it's like any other piston doing some radial walking, it just starts to get eaten up around the OD. Okay, so those are defective OE parts. And again, thanks to Jeff Stuck from Certified. He's the one that sent me all this great example stuff. Okay, so now we're going to get into a repair for this. This is a repair that Sonnax has come up with. And I don't know if you noticed this, but we were just talking about this piece being free and loose. Mm-hmm. So you see a differential between this?
I see it's a lot smaller diameter.
Right, right. So there's different piston diameters, and that gives you different clamping force for engine size. Okay, so just kind of a heads up that there is variations to that. But you can see there's more than one that's broken loose. Okay, so what I was explaining here before, what happens on the OE clutches, they dig into the housing, the anti-rattle springs break, and you get engine RPM fluctuation, you get lockup with no release, all kinds of turbine RPM rattle noise coming because all of this is being accentuated because the clutches are dragging. Okay, so what we've got, and this is a pretty extensive project for us, is that we get rid of this weld-in plate here, and we replace it with this pretty rigid piece. Part of the problem that they had was that this backing plate would flex. So we've got this design that goes into the cover. We have a set of release springs instead of the leaf springs that were in it before. Now we actually use coil springs that are the release pressure and push the piston off of this. And those pegs then fit into mating holes in this backing plate.
Those pegs?
Yep.
Get aligned with those, like they're like dowel pins in a sense, right?
Yep. Okay. So then this guy, this is a backing plate. It's going to sit here. Like yay, over the top. Now right now it's sitting a bit high, but then that'll get tacked in there. Mm-hmm. So that gets rid of the rattle because of the plates, and you still have a dual phase friction material, and you have a highly reinforced backing plate.
The surface area is a lot greater on this one. Would people opt to put one with a greater surface area in it, or are there different center sections with different size pistons? Or would you just like, is that also part of the upgrade, is to get more surface area, more holding force?
No, actually, so this is, not to confuse, but this is all OE parts, okay? Yeah, so we don't change piston diameters or the center. This is calibration.
So this isn't something you guys came up with to fix it?
No, this is
still OE.
Yeah, this is OE, but they've done variations in piston diameters depending on engine size and force required for lockup. Okay, so I would foresee there being a problem as far as calibration for lockup if you started changing piston diameters for trucks. You know, it still thinks it's got one apply area. Plus, you're talking about. I suppose you could. So I'm thinking about the future. Guys could take these off. And so, see, this is probably a gas engine with a pilot here. I'm assuming this is going to be, yeah, that's a, you know.
A lot more lug.
Yeah. That's probably a 6 lug. This is probably an 8 lug. Yeah. So this is going to be the heavy diesel. So swapping the calibration between the two, I think you might run into a problem. So now we're going to move on to 68 RFE converter. 68 RFE is a 2-path converter, And some of the complaints with this is the overpressurization or underpressurization. So overpressurization, what it does is it deflects the cover. So, and I'll show you the hard parts here on the bench in a minute, but the cover gets distorted and it doesn't get the right clutch apply angle. And this you can see, here's the clutch lining. What it'll start to do is burn from the outside and distorts, and you don't get a good clutch application. So 68 RFE, 545s, 45 RFEs, you're probably familiar with this already, but they have a problem with the TC limit bore wearing out in the pump. Well, when the TC limit valve actually controls the converter charge pressure, it does not really control converter apply pressure, which I'll show you in an oil circuit here in a minute. But if this bore wears out, it doesn't charge the converter fully and pressurize the converter. So like I said before, this is a two-path converter. If you don't have sufficient oil supply, it'll have poor mileage, it'll have poor acceleration. Because of being under-pressurized, I spoke before about the implosion in the inside of the converter, the cavitation, and any type of cavitation causes poor lube going to the cooler. You get poor lube and cooler flow. You get poor lube going back to the bushings, and it's distress on bushings and that sort of thing. So there's been a few upgrades, as you've probably seen in the transmissions. This was the original one, and that wore out the bore pretty drastically and quickly, and then they went to this one. This one lasts a little bit longer, but there too it has some bore wear issues. So anytime you're looking at the pumps on these, make sure that you repair this. There's several repairs in the industry. Sonnax has a oversized repair for that salvages the bore. Another thing to keep in mind for TCC is in the valve bodies they have the switch valve bore, and that actually controls the lockup circuit as well. So if you have, especially on the 68 RFEs, if you've got overdrive clutch failure, if you've got some of the squawks come from this, and then also the TCC apply pressure issues come from the switch valve bore wear. And mainly it's down on this end. Those three plugs are the ones that give you the most amount of problems. They tilt and stick sideways. Okay, so we're going to move on to the 68 RFE, the oil circuit, the control for the torque converter clutch. So the point I want to make here is that when it's, as you can see here, it says TC charge. That's the oil pressure that charges a converter. And the release pressure, when it's not in lockup, it is regulated and it comes off the TC limit valve. That's the one that I showed you here before in the casting that wears out. So if it's worn out, what's happening is the line pressure, and you can see the gray that moves up through here through the switch valve and the regulator valve, that is the release pressure. So all the gray is release. And as the TC limit valve wears out, that release pressure just bleeds off to exhaust, so it doesn't charge the converter properly. So when it is working properly, the TC limit controls and regulates the reverse pressure and release. And then when it goes into lockup, then as you can see here, we switch over to the red. So the red pressure, once the switch valve and the regulator valve have moved over, it's full line pressure. If you track this back, it comes down to the pressure regulator valve, comes up through the switch valve, and then it makes its way up into the lockup, the full apply side of the converter clutch. The concern here, though, is if you raise line pressure through pressure regulator springs, and you don't regulate the apply side, whatever you have on gauge pressure for your clutch and line pressure is what your converter clutch is getting. And at that point, you get distortion of pistons and covers and everything, and the life of the converter is shortened. You're running on just a portion of the lining as compared to where it should be. Okay, another way of finding out if the TC limit valve is worn is to take a cooler flow test. And what you're going to find out, and this is applies to the 545, 68 RFE, and 45 RFEs, is that when the TC limit valve is worn out, you have really low flow, when it's in the idle drive position and also in reverse, because a lot of it is that pressure and flow is leaking out through the back of the valve and it doesn't charge the converter properly. If you're not charging the converter properly, you won't have good flow going to the radiator. So doing a SonaFlow cooler flow test will pick that up pretty easily. You'll see generally what happens is as you're driving down the road when the TC limit valve is worn out is that your cooler flow gets less and less and less as it starts to warm up. It keeps on decreasing. And then generally what the guys will say is that they're losing fuel mileage if it's a gas vehicle. They're losing performance. They step into it, lockup releases really quick, and it doesn't have the power. Acceleration gets poor as well. That's when that TC limit valve itself is worn out. Here you can see the transition also in cooler flow when it's not in lockup. And then you can see you start to accelerate and cruise, cooler flow increases, and this is converter clutch off. And then when it goes into lockup, and I mentioned this before, is that see this transition from TCC off to TCC on? That indicates that the valves have moved inside the valve body. You've definitely got the signal from the scan tool. It's commanded for the lockup solenoid, and the switch valves have moved properly, and the TCC control valves have moved. So that's the transition point that you should see when it's working properly. If you don't see that transition and it basically just drops down a few tenths of gallon per minute, you know that the valves in the lockup circuit is not working properly. So if you run a few of these and you do some cooler flow tests, it's a good way to verify with scan tool and also with a SonaFlow that it indicates the converter condition, indicates the cooler condition, cooler lines, and also the valve body control. Okay, we are going to discuss another two-path. This is a 68 RFE. This is what's going into the big late Dodge trucks. You know, so it gives you the flex plate side of it. You can see now this is a gas side, so we don't have a butt plate pilot on it. We got a gas pilot on that one. Okay. One of the
some kind of furnace or something? Gas pilot?
no, Sean. It's not a gas pilot. This is a gasoline engine. You know, like petrol. That's what they say in Europe is petrol. So we just have the front end, just the cover of this 68 RFE. Like I said, it's a two-path. One of the issues with this, for one of it, is the guys taking it apart have to knock the rivets off of here. We've got the turbine and stator out of it. Impeller side here is gone. So this is just basically the OE piston and the cover. This is the OE friction. It's a two-faced friction. You can see it's got scallops out of it to improve flow across the face of the lining. Okay, and then this is the cover itself. Okay, so one of the issues with this is, just like we talked about before, is distortion, and you might be able to see just a little bit of the start, but there's a pad here, there's a pad here, and in time what it does is these raise up. You can see just a little bit of it here and there with kind of the glare, yeah. And when that happens, the surface contact and clamping force of this disc doesn't hold properly, and it runs out, it will not lock up properly, and starts to set lockup codes. So that's part of it. The other issue is piston deformation, and in the PowerPoint I explained how lockup apply pressure is not controlled. It can go, when the guys start amping up apply line pressure in that, and they hit the, over 200 psi, this piston does not like that, and it starts to deform. And you can see it a little bit in this one. This one isn't quite as bad as normal, but they'll get excessive run out because it's no longer running flat. And when that happens, again, you don't have lockup. It'll run through the converter, slip through it.
So a torque converter rebuilder, will they mount that on like a turntable and put a dial indicator after, just to see if that had run out?
Right. Good comment. So yeah, they would put it on a turntable, spin it up, and Generally, before they even do that, they're going to probably chuck it up in a lathe and just try to take a face cut on it, you know, set it in. Yeah, and then they'll be able to see it when they come up with the tool to find out. I mean, if it's pulsating, running out fore and aft, or it's deflected. So again, I mentioned this before, but basically these converters are made with, they're either going to have a 1 to 3 positive angle on the cover, or they're going to have a 1 to 3 angle positive on the piston, and that ensures that the piston comes down onto the lining on the outside first. Okay, so as these get overpressurized, you can almost see here what would happen is this piston's going to collapse down into the inside, and it's going to start to lock up on the inside of the ID rather than the OD. And you'll never get full clamping pressure, because as the pressure increases, it just keeps walking away from the lining. So here you can see on the inside, on the other clutch pistons we talked about, the inner seal. This is where the inner seal would ride, right here. There's going to be a Teflon and rubber seal there. And the turbine shaft is sealed by a metal clad seal in the middle. So this brings up another point, is that you have to have the right amount of flow going in and out of this center. You know, I missed that I didn't speak about it on some of the other converters, but if there was a thrust washer there before and then somebody cuts it down, puts a bearing on it, or vice versa, they put a thrust washer on that doesn't have any oil grooves through it, that changes the whole apply and release factor of the converter. So if you think about it, if you restrict the oil flow coming out of here, when you first start it up in the morning, you don't have good enough flow to lift the piston off the cover. Does it make sense?
Yeah.
Okay. So then when it takes a while to lift that off, and while that's happening, you get the engine surge and vibration and all this type of thing, RPMs going up and down. Well, the opposite happens, that if you put in the wrong washer or you restrict the flow up here, when it does go into lockup and this oil is supposed to vent, it's real slow in venting, and it's real slow on the apply pressure pushing it down. So there you get this spin up on the other side of, you know, when it was trying to do it in 2 or 3 tenths of a second, now it's spread out to 5 to 6 tenths of a second, and it doesn't lock up properly. And then the RPMs go up, and then you get your code, your 740 or whatever. And so then at that time, that's when it starts to burn and glaze the outside of the lining. And then, like I mentioned before, once it's glazed, and then it loses its absorbency to fluid, and it's kind of a downhill after that. It overheats, and then the lining starts flaking off of the backing plate or the clutch plate itself. So, okay, so we started out with this 2-path, gave you some examples of failure on this. And so this is a heavy billet cover that Sonnax makes. It's a replacement. This is the clutch lining that we've got. Okay, replacement for OE.
And then what are the grooves cut out for like that?
Basically the same as what we were looking at there, and that's to give it more oil flow across the lining. Okay, and so this oil will be sitting at this location. So now when it's going into lockup, the pressure is going to be pushing from the outside, and it's going to be trying to go from the outside to the inside. Okay? And when it's being released from the inside, the fluid and flow is going from the inside, bleeding across there, giving it release. So basically it's almost like an orifice, you might say, you know, for apply and release of the oil flow across the lining.
And the purpose of the tiny hole they drill in those pistons?
Okay, well, a lot of times it's to help just to keep the piston in a I guess you might say a controllable steady state, almost like the balance pistons do in the late model transmissions. Some of it is it helps to keep, so once it's in lockup and it's applied, the oil is pushing again from this side of the piston. Okay, and that little bit of oil is allowed to come back here and keep it semi-lubed and allow it to release faster, you know, once when it does have to go the other direction. So there's a couple, actually I mentioned it in the PowerPoint, like the 5R55W does it. There's the actually AX4S's used to do it, where they had it's like a backfill valve, and it keeps back pressure on this side of the converter. So like say a 5R55W or whatever, they actually held 5R55E and the W's held about 5 psi on this side consistently all the time, and they did that just to control. And so when it goes into lockup, it was relatively smooth, and when it releases, it's relatively quick. So on an E, 5R55E or W, if you disable that, then you have just turned it into an on and off type converter. So that was one of their earlier stages, you might say like a PWM type of apply, because they had pressure on both sides. So yeah, GM did this for a while. They've drilled a hole in there. 4L60s had that. GM has gone to the hole and then taken it away, and vice versa, back and forth. Generally, when General Motors had the woven carbon lining, they didn't need that hole in them anymore.
By keeping the circuit filled and primed, it's like almost immediate. As soon as they go from apply to release, they can start doing what they need to do. Whereas if there wasn't any volume of oil in there because it all drained back, then you have to deal with a new inrush of fluid.
So again, going back to that point, because I've done so much work with the SonaFlow, you can actually see that transition, is that if there's a void back here, and it takes a while, because if you think about it, the pump has to make up for the volume of this when it's going to go from one direction to the other. Mm-hmm. You know, I don't know what type of volume you're thinking of, but that small 20 to 30 thousandths between here and the cover has to be filled and have to push it off, right? Okay, well, if you have excessive clutch clearance, or this volume is completely zero, and now when it goes into the release side, you can actually see your cooler flow dip way down as that pump volume is trying to charge that thing up. It takes that much extra time for everything to be charged and filled and to get the piston to move. So you can see it happen, that event happen in the cooler flow.
And then the bolt, like, it looks like the center hub of this has bolts instead of the original rivets?
Yeah, and that is just basically to make it easier for the rebuilder, so it's less time consuming for them to stamp rivets and put it back together. And next time, okay, so you get in there and you put rivets and you stamp them in like the OE had, okay, the guys had to cut them off. Well, if this is going to be rebuilt and you get the hot rod guy, and after so long he's going to put in new lining and take it apart again, they can cut, you know, the OD and replace that, save the cover. But if that was stamped with rivets, then they got to get back in and remachine it off. So now they can go back and reuse the cover again. Easier to rebuild. So this is a 62 TE, and we were just talking here that a lot of the commercial vehicles have gone to this. I believe the Postal Service has gone to using it, and they're working pretty hard. That's part of the issue. The other issue is that they get overpressurized. And if you're familiar, that this valve body, the good old 41 TE and the 62 TE does not have a converter pressure limit valve in it. Okay, so it can ramp up, and as the valve body wears out, we know that the pressure regulator valve bore wears, and the line pressure can go high. It actually starts to deflect the piston. So this is a piston that's in relatively good shape. If we were to run a dial indicator around it, you probably would find some run out, and you can also see that it's actually starting to if you can see by the shadows, you see that it doesn't really look very flat. If you can see it, maybe by some of the shadows, that it has basically run out. It has high spots and low spots in it. Okay, so it hasn't failed at this point. So that piston then would have been running against this bonded lining. This lining is bonded to the cover. We talked about it a minute ago. Okay, and you see how dark it is? So it's already glazed. Glazing means that the properties of wood fiber is it allows automatic transmission fluid to be absorbed. It holds that automatic transmission fluid in the fibers. So It allows the cooling and somewhat of the slip, and then this one also has oil flow grooves going through it. Well, once the lining gets glazed, it's basically burnt. And so now the absorbency from the ATF into the wood fibers is gone. So you don't have any adhesion, you might say. It has the oil will be trapped at the surface, and it just keeps burning itself off, and it's a slow degrading. And you can't hold the slip rate down, so now the torque of the engine runs away and the lining won't hold. So this is the beginning of it. You probably remember the days where people would run too long a bolt through the flex plate, okay? So as long as we have this cover, what you should really do on these before you ever put a converter back into a transmission, or you've got a failure of some type, is just look into the hole and make sure you don't have the dimple there.
See, there's no contact.
Yeah, because that contact transfers to the inside and ruins the lining, okay? And it ruins it quickly. Okay, set that cover off to the side, set this piston off to the side. These are the components. Okay, so here you can see the damper spring. Damper spring locks into the turbine like that. And then this would be, sets together like that. Okay, so now we've gone through one that is fairly good. Now we're going to get into one that, this one has definitely failed. The clutch material is completely gone. The cover is failed, is not usable, because the converter rebuilder, what they will do if the cover is good, like we had here, I'll go back to this one. With this cover, the converter rebuilder would go in there and he's set it up in a lathe or put it in a CNC, and he'd trim off this material. Sometimes they'll use media blasting, bead blasting or something to remove the clutch lining too. There's multiple ways of doing it. So they'll be able to salvage that cover. This one is beyond that. You can see that the material is so thin to begin with that they can't get a good surface back from it. It's actually chewed into it. So Sonnax does make replacement covers for that. And then we also have replacement pistons. And this is one of the biggest problems, is there aren't any pistons, not many pistons in the field that are in good shape anymore. Okay, so this is a billet piston that we've got. And what the shops will do then is they'll pop the rivets out of there and they'll re-rivet the damper assembly onto that billet piston. Okay, these pistons are deflected because of being overpressurized. Like I mentioned before, is that the 62 TE doesn't have a pressure regulator limit valves.
Normally, like the pressures, assuming, I mean, they pretty much run the same as like the 41 TE, that with the variable line pressure option variations, they still kind of run like and drive at least like the 140, 150, and then drop down from there. Mm-hmm. But you're saying if the pressure regulator valve wears, the pressures will end up climbing higher than that, and is that what, is that the root cause of this, or is it just overloading? Because like, are these built too weak to begin with? Yeah,
I would say, Sean, all of the above. The material was probably not suitable for the torque load they were putting into it, and the other part is the valve body does wear out. The pressure regulator valves wear out, and when PR valves wear out, they generally go into a high line condition. I mean, pressure doesn't decrease, it actually always increases. So when they go into a lockup condition, like I said, there isn't a limit to it. And so what the maximum is, I can't really say what they designed this at. I know the GM piston was GM 4060Es, 4L60s, that type of thing. GM has told us that their maximum pressure, they designed them to run at 130 PSI maximum. Anything beyond that causes a distortion in the angles and the piston, okay? So I would imagine, I mean, you start running these, 125 to 140, whatever it might be, and eventually it starts to degrade the lining like we had here, and then leads to catastrophic failure like that.
The way Chrysler had their line pressure set up is they always had higher line pressure until they came up with the variable line pressure solenoid, the VLP. Mm-hmm. And then they were able to pull it down, I guess for fuel economy reasons, but my guess is they will raise the pressure up quite a bit, or you know, to their max, which isn't extremely high, but high enough, higher than these can handle. Whereas we think of like some transmissions, like a GM, that when you're wide open throttle, you got 250 psi or 200 or maybe 200 psi, but they never deliver that 200 psi to the converter. So they have valving that prevents max pressure, line pressure, from getting to the converter, whereas Chrysler is just letting line pressure get to the converter. And
Right, right. But so in saying that, and so I don't walk over it or we don't forget it later on in the GMs, is that in the 4L60s, it was common for the guys to block the converter regulator valve because they wanted to get rid of slip. Well, when you do that, you are supplying full line pressure to that piston.
yeah.
And that's an example of, we can get into that with the GMs, but so I don't forget, that's a situation. And in the video, or excuse me, the PowerPoint, we talked about the 5R55Ws. That's another one where the guys are modifying there's a pressure TCC modifier valve. And if you increase that too much, it distorts the cover and the pistons and takes them out relatively quick. So the converter rebuilders have really had a problem with that 5R55 N and S. NS and W, actually all three of them, by the guys jacking up the pressure.
So on the 62 TE, that piston, that would be considered a modification that probably should be done on, obviously these aren't typically modified vehicles, ProMaster vans and stuff like that, or Caravan, but this would be, if you've got a customer that's going to be like hauling stuff in their ProMaster, maybe a plumbing company, they really should be putting this kind of stuff in there.
Right, yeah, they should be putting it in. As an example, I mean, I see the weekenders with the caravans, and they've got the the travel trailer and all that kind of stuff on the back. Those are the guys that really should be having this, because they're heavy into the throttle, pulling that thing pretty hard, and that's where your maximum line pressure is going to be at. They're going to start to be deflecting that. So, yeah, it would be worth, in my opinion, it's worth the money to amp up a bit and ask for a heavy-duty piston in them. Okay, so now we have another upgrade we're going to talk about. This is the 4748 RE. This is a billet cover. You can see that's a pretty solid piece of material.
MP.
MP, yep. I know what that stands for. It's somebody's sample, actually.
Oh, okay.
Yeah, but as long as you pointed that out, Sean, we talked about this the other day, and so the difference between this pilot, that's the pilot that rides in the back of the crankshaft for the guys in the shops. This is called a butt plate pilot because it physically butts into the back of a diesel crankshaft. And this stops the deflection of the converter. It cannot grow in this direction because it's stopped by the crankshaft. So a converter, in a conventional converter for a 48RE, it has to grow from here to the outside. And that's why on the conventional 48RE that has the pads out here, the pads start to deflect on the inside. Well, that is not going to happen with a billet cover like that. Okay, it's solid ring all the way around. And with the massive material, we showed a cutaway of this in the PowerPoint towards the end on the slides. We took a slice of it, showed you how thick it actually is. So this is a 48RE upgrade, and the way this works is basically you've got a solid, see how heavy that damper is, damper assembly and plate. You can see the amount of surface area and material in this is really pretty extensive. So now you've got, instead of one clutch disc that was in the original 48RE, this is designed to go to some pretty high horsepower, high torque load vehicles. So now you got a 3-plate, and then this is the piston and the damper assembly that sits on top of it, okay? And then these lugs match up with the internal drive lugs, and it stacks together like this, okay? It's a pretty heavy converter by the time you get done, but it will take some torque load.
Are these modifications being made because people are chipping and tuning their trucks and the 48RE is not able to handle it? Or like if you had a stock configuration vehicle and you just did normal stock stuff, I know nobody does that with diesel trucks anymore, is this much of an upgrade necessary, or is this really for the people that are tuning their trucks and having more torque?
Yeah, well, it goes back to the same deflection. This is really made for heavy working. I mean, I guess we would call them the grocery getters. They probably don't need to do that. You can go back to a stock converter. But again, when the guys start raising line pressure and putting more, engines are bumped up and all that kind of stuff, you're just putting more torque load through it. With a single disc, it just can't handle that. And with a single disc and the torque and the distortion we talked about before, it ends up starting to slip and to run away. So the other thing, so we don't forget it, but a 48RE, does not have an apply pressure limit, okay? The switch valve, the converter regulator valve, switch valve that's in the valve body on that, it says that it's designed to limit, and it somewhat cuts back pressure in reverse, but it really doesn't do anything in the drive lockup range. And it does it through the differential in the spools. So you can still get high runaway line pressure on a stock converter, and then it just distorts the piston.
Get yours today at Sonnax.com.
Yeah. Okay, we're going to go into the Ford 2-path and the Ford 6R60 and 6R80. Now again, this is a 2-path converter, so you've got clutch apply pressure is coming in and clamping this piston here and onto that clutch, which pushes the clutch then onto the cover, okay? And in release, you've got converter release pressure going down where this arrow is at. So this arrow is a phenolic or a plastic cap that actually goes onto the turbine hub, and the turbine shaft is right there where the end of that arrow is at. So if you have plastic in your oil pan when you're doing a transmission service, or you're doing an overhaul or whatever, and you're wondering where it came from and nothing inside the transmission has any plastic that failed or whatever, it's probably coming out of this torque converter. So this gives you an idea what that looks like. Also in the 6R60, you can see this clutch lining has scallops or cutaways, and the oil, it's designed that way so that when it's in lockup, you still have oil flow going across the clutch. So this is a clutch that's composition paper material. So anytime you have paper, you've got heat buildup if it was 1-to-1, because paper is a sealant, and paper also does not conduct heat. So the GM woven carbon lining, the reason they use that woven carbon is because carbon will transfer the heat from both the turbine, the clutch, and the cover into the cover and dissipates that heat. And paper is an insulator. So it insulates the heat between the two items, and the heat continues to build up. So that's the reason you have to have these scallops, or this oil film runs across the lining in order to dissipate and take that heat away from it. But as I've got noted here is that these segments, they start to flake off, and that will end up in your oil pan, and then they lose lockup. They won't have converter clutch apply anymore. 6R60 and 6R80, this is basically about the same as what I showed you before on the ZF8 speed. Is the TCC release pressure is right here at this WK pressure tap. It's the only pressure tap on the 6R60 transmission. And I've got the specs here as far as what normal pressure should be. And this is the only diagnostic pressure tap on the 6-speeds. What you'll notice is that as the valve body wears out, this pressure starts to vary at an idle. And this pressure will go up and down and up and down, and the engine RPMs will follow that pressure. So if you're looking for a converter clutch that's crowding or semi-applied at an idle, you tap into that, and again, this is the pressure that you should have, but you'll a lot of times find out that it'll vary. And here I've got it listed 76. When it starts to wear out, you'll be in the 45 to 50 psi range at an idle, and it'll vary up and down. And the converter clutch will be going on and off with that same engine RPM. So this is two-path cooler flow, and this is also ZF6. This is taken out of a actual ZF unit. It's from an Audi, but it's using the SonnaFlow again. And this is cooler flow from 6R60, 6R80. You can see here you got park, the differential between cool and hot, cool, idle, in reverse. Here we've got drive test, TCC off, and now here you can see TCC apply. So that differential, again, is telling you that the valves have moved properly, that the clutch is actually changing position, and that the flow across the clutch is correct. So what is an indication of what the SonnaFlow will tell you. Okay, we're going to move on to the hydraulics for the two-path, the Ford 6R60 and 6R80. The point that I need to make here is that how critical bushing tolerance is, and I know some of you guys are working on you've seen the bushing wear in stators and that throughout the transmission. So excessive bushing tolerance reduces lube oil pressure. Lube oil affects clutch and balance pistons. So the balance pistons are the timing device for these 6-speeds. As that compensator oil in the GM or balance oil is lost, it changes and affects the shift timing, and a lot of times that's misdiagnosed as lockup converter clutch apply. So the point I wanted to make here also is that if you look at the oil circuits, there is here's the lubrication control valve that controls the pressure to the lube circuit. If that's worn out, it affects the converter clutch apply timing, and it also affects the flow going through the transmission as far as the balance pistons. Okay, and the other one that I wanted to make a note of here is the solenoid feed pressure. That actually affects the converter clutch apply, because solenoid feed pressure feeds the lockup solenoid. That's fed right here. Lockup solenoid, here's the output of the lockup solenoid going to the bypass clutch, overdrive clutch pressure control, mainline pressure, converter release, and all of that is all affected by solenoid feed pressure. Solenoid output here is also affected by the dampers. And the dampers, as I showed you before in the ZF8, the little rubber diaphragm wears out in those, and then oscillation effects come off of the solenoid, and the valve control degrades. These are the valves in the 6R60 and 6R80 that affect the converter clutch. We've got them highlighted here. And so if you're doing a vacuum test, you can go to the Sonnax website and we show you what all the locations to vacuum test, what's good and bad vacuum readings. I just made a note here, this accumulator is not in the 6R80. And these are the accumulator pistons that I showed you before, these little rubber diaphragms that wear out. And we have a repair for that. We replace them with a spring and a piston assembly. The solenoids I've got indicated here. So each, these are the lockup control solenoids. Each of these has a red star. These are the solenoids that affect the converter clutch. And you've got 6R80, 6R60, and the ZF6 version. ZF solenoids here, 6R80 on the top, and the 6R60 here in the middle. Okay, we're going to take a look at this is a Ford 6R80. There's multiple versions between the 6R60, 6R80. 6R80 even has a later model than this, a captive clutch assembly. That's more complex than this one. It's been very problematic too. So just disassembling this here, give you an idea. It has the same, pump impeller, still have a stator, turbine. Now this is a sample. This turbine has been, it is initially riveted on there onto this turbine hub. The turbine hub in this case is, as you can see right here, goes through this drive damper, which is pretty unique. Okay. And that's riveted onto it. Okay. stacking up parts here. Okay, so this is the piston. And here you can see this is one type of captive clutch. This was riveted into the cover somewhat close to what we had on the GM captive clutch. And it's also kind of a takeoff of some of the ZF captive clutch designs. So this piston, the cover has a guide that you can see that guide then runs here and centers the turbine hub, this bearing. Okay, keeps everything straight. So in saying that, if you look at like say the ZF 6HP has it has a stator bushing and it has a front and rear stator bushing. And if you look at the Ford, it has a rear stator bushing, which is the internal bushing, but it does not have a front stator bushing. And this is the reason it doesn't have a front stator bushing, because this is centering and piloting the turbine shaft. Okay? So in thinking about that, you know, if you have any center line, you never have three different bearings. You have a bearing on end or a bearing on the end, and you don't have a bearing end, middle, and end, because then they fight against each other, and shaft ends up breaking a lot of times. But so this Ford is different than the ZF in the application that they don't have a front stator bushing, and this is the reason. Okay, so this is the clutch. Here again, this is a paper wood fiber, okay, and it's a dual-faced clutch element. Rides against the cover like this. Okay, and this is another one it's very complex for the converter rebuilders to rebuild it, because trying to get that clutch back clearance back to where it should be, you know, the piston travel and everything, once you've cut the rivets off of these, and you've taken material, like say off the piston, you've rebonded the clutch plate, and Sonnax supplies these clutch plates pre-bonded already. But if you took any material off of there, off of this, or off the plate, you've now changed the internal clearance. And the stack up height is all done by the build off of these pads here. Okay. Okay, so this remains at a consistent height. And if you take material off, now you've changed the clearance. So here again, you can see the oil flow. An illustration of this was also in the PowerPoint with a different type of converter, but you can see Ford is still using that oil flow through the clutch lining.
Looks like termites got to it.
Yeah. Yeah, I'll grab it for you, Sean. So the ZF 6HP and this one is another one that's very difficult for the rebuilders to get stack up height and clutch clearance and everything back to where it was OEM, because they've had to cut all this apart in order to just get at it to replace the linings. So it's really been a challenge.
Does Sonnax, what all do they make for to rebuild this converter?
To rebuild this one, we have the bearings, we have the clutch lining, we've got stator bearings, we've got stator rollers and springs for the inside of the stator, and I believe we have the turbine hub for it.
So what is the most common failure that you guys see in this torque converter?
Okay, I would say most common failure is clutch lining failure, which is burning the lining like we talked about before. Wood fiber doesn't take a lot of heat, and if you have any slippage, it starts to burn the lining off. So the source of that problem, though, is mainly the valve body itself, and we went through that on the PowerPoint. But as the solenoid modulator starts to wear out, you don't get good feed to the solenoids. You have the between the solenoid and the actual shift valves, you have that small little black plug that leaks between the two of them. And then you've also got a converter regulator valve that the bore wears out on that, and the pressure regulator valve bore wears out. So most of the degrading of the lining comes from the hydraulic issue inside the valve body. Okay, on to 722.6, and the reason I've got this one in here is just, this is an older transmission, of course, but again, this is a 3-path converter, and the point I'd like to expand on is because this one is very easy to test the clutch that's in the cover through the turbine shaft. So when you've got the converter on the bench and it's all welded together, it's going to look like this. Which you can do in the shop, you can take the turbine shaft, which you've got right here, and you can pressurize it through the feed circuit. And when you do that, the clutch that is in the cover here should apply. When that clutch applies, you need to make sure that you don't have any oil pressure loss right here at this area, because that will cause the other containment oil, the release oil, to enter into the clutch and crowd it. And there's a problem with the 722.6 having a shutter condition when it goes into lockup, and that's caused by this cross leak. And so this is that pilot, the turbine shaft that I showed you in the previous picture, engages and fits right in here. And from OEM, there isn't a proper seal at this point, and it starts to wear out. So Sonnax has an upgrade that the converter rebuilders replace this pilot, and it's got improved seals on it to isolate that release circuit from the converter clutch apply circuit. Okay, so we're going to take a look at another 3-path. This is Mercedes 722.6. Okay, here you can see again furnace braze fins. We got stator, we got turbine. Flip this over, and here we have clutch assembly. Okay, so again, this is 3-path.
You might mention that came from here, and I lost a snap ring.
Okay,
So.
Sean has a displaced snap ring. Not the end of the world, we can find another one. Okay, so just a few critical things with this 722.6. This was in the PowerPoint there towards the end of the PowerPoint, but a couple of things that are really critical is, actually you can see these are original Mercedes plates. I can see the Mercedes insignia on there. Okay, and there's other plates out there, and there's been a lot of problems as far as lockup shutters and plates dragging, so that they do not want to apply and release. The oil flow in the material is really critical on the Mercedes, just as an FYI. So you can avoid a lot of problems just by putting in the proper or original clutch frictions. So the other point that we made in the PowerPoint is the problem that they had with this 722.6 is what we just talked about on all the other 3 paths, is that you can't have fluid pressure from charge and exhaust converter pressure merging and blending into the apply circuit. And the 722.6 has this pilot on the front cover, so I'm going to knock this out. Maybe.
Oh, yeah. Wow.
Sorry, Sean. Okay, so this is the back side of the piston, and it was living here until we made a mess to get it out. Okay. Now this centered device, if you look at the other side, it's actually crimped in here. I don't know if you can see there's crimps on 3 sides.
Yep.
So they push this device, this centering, it's aluminum piece, they push that in there, and then they crimp it on the back side to hold it in place.
Yeah.
Okay, so in the remanufacturers, what they do is they'll come in the front side, cut the whole thing out, and then press another one in there and also crimp it. But what I'm getting at is that the center of this wears out, and we have a replacement that has a seal on the ID, a seal on the OD, and stops that crosstalk and that cross leak, because it was a big problem for crowding. And then we also have a spring set in the clutch pack that we have that goes between the steels and releases the clutch at rest too.
That's the thick one. Flip it over. Newbie.
Okay. There we go. You learn something new every day.
Now, here, I got a question for you. Because, we here at school, I talk about this stuff, and I use the literature that they've got from Chrysler on the training. And they say that the converter never locks up, and it's always slipping around 95% or something like that. Is that true? Or that you found? And then also, how, because these are just the paper type clutches, how could it handle that? Is it just because of the oil grooves? They'll pull the heat away well enough?
Right. So this always has oil flow going across it, because the rest of the converter is charged.
Yeah.
So it is forcing oil across this surface all the time, whether it's in slip or not. And yeah, they can control the slip rate just by the amount of pressure that's being applied to that piston. So right, it can go to full lockup or semi-slip at any point. That's the great thing about a 3-path converter is you can slip the clutch as much as you want and you're not going to generate heat in the rest of the unit. When you have the 2-path, and that's what we talked about before, you've got the paper lining that isolates the heat, doesn't carry it into the cover and the rest of the components, or you've got the woven carbon and that dissipates heat, it transfers the heat into the cover. So if you continually slip a 2-path converter, it generates heat. And the great thing is here, these are controllable, plus they don't have the heat. It's got a constant flow going through the converter.
These dampers are so much smaller than on like what we see on most. And they're all located towards the center. Is that, does that end up being an issue ever with these that you think of?
No, I have never heard of or never seen a spring damper assembly problem with a Mercedes. It's surprising, isn't it, as small as what it is?
Because they basically use the same converter in the Sprinter vans and, all the way to the Jeep.
All the way through the Jeep, 722.6, the high horsepower, the high torque diesels, yep.
So here we have 6T70, which is very close, basically the sister to 6T40s. And the failure that we have with these is twofold. Really, the inside pilot of this piston wears out, and so the sealing ring, which I'll show you on the bench, leaves a groove in it, and then it doesn't want to lock up properly. The lining will start to come off. This is a carbon woven lining, and we'll show you more of that on the bench. And then the other problem that happens with these is that on the damper springs, they have stops on them. You can see about in that area. We'll give you a close-up here in a minute and show you where the stops are at. But these spring stops are breaking out, and once that happens, this outer ring of this damper that's riveted on, it loads up with metal and material. So that has to be taken apart to be cleaned. Okay, 6T40, 6T70, mainly 6T40 that we're showing you here, has a couple of issues that during the rebuild process you have to be careful of. This is support. This is the sealing. There's a metal-clad sealing ring right here. It's actually a lip seal. And when you put the bell housing with the pump assembly and the idler gear assembly over the top of it, it's pretty easy to deform the metal area of this lip seal. If you do that, you'll lose lockup. And then we also have there's another turbine shaft's lip seal that's inside the turbine. This is a turbine right here for the 6T40. And as you put that torque converter over the top of the turbine shaft, you can do exactly the same thing. And as that lip seal will get deformed, and then you'll lose lockup. So here's two areas within the 6T40 that you can cause during rebuild that will lose torque converter clutch apply. Okay, here in the 6T40, 6T50, we've got the air test that we showed you before. Same air test for the lockup valve we showed you on the 6L90, 6L45. And this is the valve that it's stroking, that when you apply air pressure there on the case, it will stroke this lockup valve up and down inside the pump. That verifies that the lockup valve is actually stroking properly. And here's a close-up of the window that I showed you before. We'll show you some more on the bench in a couple minutes. Another thing, so that I don't forget, is on the stators, if we were talking about contamination inside the transmission, again, if you have aluminum, the stator is generally the only aluminum component beside the fins. What'll happen is, here's the roller clutch. The rollers, what they'll do is they come up and they semi-tip sideways. So if you can see this oval, it's not really a round circle. The roller comes up, contacts the stator cap and tips sideways, and then it more or less smears or skips for a bit, and then eventually it starts taking material off, and you can see the wear around the outside radius of this stator cap, and I'll try to show you another one here in a minute. Okay, here's the valves in the 6070. This is a Gen 1 that you need to pay attention to if you have a loss of lockup, and this is a TCC control, and this is a TCC regulator right here. Both of those, as far as a lockup condition, you should check those two first in the valve body, either visually or vacuum test. The next one that you want to check is this in the small casting. There is sometimes there's accumulator bore wear, but the main issue is the AFL valve right here. This bore wears out probably first of any of the valves in the inside. And then the next in line as far as inspection, they have these the clutch regulator, clutch boost valves. That's these guys. This one right here, and also that one there would be the next sequence as far as bore wear. Okay, we're going to go into some of the Toyota units, and this is front wheel drive and rear wheel drive units. One of the big things with Toyota that I'd like to mention is that the solenoids have so much effect, and they control so much as far as the converter clutch and shift quality. The solenoids are really susceptible to wear, and you see right here, this is the U660 and U760 solenoids, the TCC solenoid and also the EPC solenoid. Now they have this little coated pintle assembly that runs within this plunger, and here's the coil, here's the canister, and this all loads up with, as you can see here, we call it permagunk. Basically all the material that's coming off the planets, the planet pins, as the converter fails, whatever it might be, all of this fuzz, because this is a magnet, ends up in this canister and starts to wear out the insides of the solenoids right here. And on the ends of this solenoid, there's some really small microscopic little balance holes that fill up. And as they fill up, this plunger does not travel properly within this sleeve right here. Okay, so a precaution on this also is, you see this rubber diaphragm? You have to be really careful when you run that as far as the solvent tanks or whatever, it'll distort. So if you're cleaning these solenoids without taking them apart and you put them into a highly corrosive type material or whatever that would eat up the rubber, it'll take this diaphragm out, and that'll also negate the control of that solenoid. When these get really high in mileage, what you'll find out is that this, we call it the manifold or the snout, that actually starts to wear out too. And on our Sonnax website, we have vacuum test information, so you can actually vacuum test this right in the valve body casting, and that isolates whether or not this manifold is worn. Okay, 09G TF80s, the TF70s, TF81s, actually even the U660s and U760s are really susceptible to the converter clutch control. So people misdiagnose them as having a 2-3, a direct clutch failure or whatever it might be, or a torque converter clutch issue when it's really a solenoid problem, solenoid timing issue, that it cannot bring the converter clutch on and off. So if the converter clutch is stacked on top of the shift, or it comes off too early during a shift, what ends up happening is you have this flare or a bump condition. So it can be really tough to diagnose or isolate whether it's solenoid, whether it's a pressure issue, or a converter clutch. So just keep in mind that solenoid control is really critical for torque converter clutch on these units. And here's another example. This is actually data taken off of a valve body test machine, and it's the differential in solenoid pressure. So you can see one of the other things for all the Toyota units and all the Asian Warner units in the valve body, they have, here it says solenoid pressure.
solenoid pressure is, on GM, it's actuator feed oil. On Toyota, it's a solenoid regulator valve or solenoid modulated solenoid pressure. And as that wears out, it affects the feed to the solenoids themselves. And when that wears out, you've got a differential. And this is the indication here that you can have with a worn solenoid modulator circuit. You see the yellow and then up to the red one here. So that is a variation in clutch pressure. So as far as your adaptation for the computer, it can only adapt so far. And if you have a variation of points that broad, here you can see we're probably looking at about, even about 30, 40 psi of clutch pressure variation. The computer can't adapt to that. So your overlap between the converter clutch apply and release and clutch timing is way off. So if you put a new solenoid in it, it's not necessarily going to fix it. You have to go back to solenoid modulator. Okay, here we have indicated the solenoid modulator valves and the lockup valves, the ones in the valve body on the U660, U760 that control shift timing and lockup control. And this is on the Sonnax website. You can just go on and download it. We also give you all the vacuum test locations for all of these valves here as well. Okay, 5R55 WS&N has a problem with converter clutch piston deflection. So I put this in here just to show you that this is the clutch, and as you raise converter apply pressure through various means, modifications, it starts to take this piston and it distorts it, and it'll push it out in the middle, and then it instead of clamping on the outside, it should originally come down onto the cover and start to touch here first. And then as the pressure increases, then it spreads across this piston and seals it off. Well, when you raise the pressure too high, it distorts this and it turns it the other way. So now it starts to apply in the middle and it doesn't get full surface contact as the pressure increases. So raising the converter clutch apply pressure on these units, 5R55 WS&N, distorts the actual cover of the converter, which is the crankshaft side here, and it distorts the piston. And these are the valves that on the 5R55N, W, and S that control this. This is the converter clutch control, and then this one in the blue here. That is actually a back pressure valve. So when this goes into lockup, it keeps a constant pressure between the piston and the cover. That's this little plunger assembly that's right inside that blue circle. Okay, and this is in the red here, this is a pressure modifier, and this is the one that's frequently modified, sometimes to increase apply pressure and salvage the bore. The bore here actually wears out, and as that happens, if you don't restore this back to OE and you increase the converter pressure, it will actually start to deflect the piston that I showed you here before. So you have to be careful that, especially on this transmission, because the converter is not that strong, that you restore this pressure to OE. And this is that bore, the TCC control. You can see I just have the variations here. There is 2 different diameters for this modulated circuit. That takes EPC pressure, and as EPC pressure goes up, it pushes in this TCC modifier modulator valve and increases the pressure that's going to feed the converter clutch apply. So if you increase this too much, your apply pressure goes up at the same time. Here I've got some cross cuts on torque converters, and I just wanted to show you, this is an OE converter cover, and I'll show you some more of this on the bench here after a bit. This is very typical what used to happen in the early Chryslers, some of the Toyotas, where the flex plate, flywheel flex plate bolt to converter was too long. It would go through the pad and then it would put a dimple on the cover. The other issue that you run into is that as you overpressurize the converter, it starts to distort the converter at this side, on the flex plate side. It expands that, and it changes this contact surface of where the clutch applies. This is the clutch apply surface right here. This will get distorted, and instead of being flat or having a 1 to 3 degree taper, it distorts and deflects this direction. So in the aftermarket, there's these heavy covers made, and you can see how much material is here, and it eliminates that distortion and the flex that would come from the cover. Okay, converter damper issues. Now the damper, I'll show you some more of these on the bench. This is typical for the Ford 6F35, the GM 6T40 and 6T70s. This is a damper assembly that's inside. So the clutch piston is riveted then at these spots around here. We'll show you on the bench. But basically these stop pads for these springs wear out and they break off, and then contamination goes through the entire converter, and that contamination gets stuck underneath this damper assembly, this plate you can see right here, and then it loads up. Here you can see a broken damper spring. This is a 6F35, and the stops on the end of the springs break, and then the springs come loose and they go up through the cover and contact the cover and start making material. Okay, here we have the ZF9 HP, and the point I wanted to make here is, see, this is a paper lining. You see the oil grooves for oil flow. So when this is in lockup, it has continual flow going through that lining to cool it. And then also there's the issue with the segments. Here you can see the segmented lining, and sometimes these corners will curl up, and when that happens they start to flake off. So if you see clutch lining in the pan and it's not relative to the transmission itself, a lot of times it's coming out of the converter. This lining is, the puzzle lock has started to come loose. The other point I should make here is these have long damper springs. You can see it winds all the way around the outside from one end to the next. And what happens with those is the damper spring starts to wear on the outside of the damper itself, and eventually either the spring pads can break, or because spring material, as you know, is very hard material compared to the surface contact around the outside, it'll start to etch, and then that material will get into the pan and then into the solenoids. Okay, the last couple slides that you have here in your material is just terminology, and it's definitions of what some of the things we talked about here and what we're going to talk about on the bench as far as clutch, slip mode, captive clutch, dual dampers, and all of this type of thing. I also will mention that there is on the Sonnax website we have many technical articles, and one of them that is specific just to this terminology is torque converter clutch control, and also torque converter clutch hydraulics #2. So you might want to look that one up on the website. And the next slide has that information on it, as well as definitions for the cooler flow, head pressure, how to isolate with the SonaFlow. We've got that information in there. We've got information on cooler testing, and all the terminology that I talked about here previously. That's all on our website. Okay, thank you very much. Appreciate the attention.